Good day everyone. In this video, I'm going to be explaining everything related to electricity. This video is a summary of calculations in electricity. So I'll be moving through concepts very quickly. So we have time for calculations. Now, if you're writing exams like Jamb, eᵣε₀A, or NECO, this video is for you. Electric charges. We have two types of charge, positive or negative. Positive charges are called protons, negative charges are called electrons. The charge on an electron, right, is the charge which an electron carries is given as negative 1.6 times 10 raised to power minus 19. While the charge on a proton is positive, is plus 1.6 times 10 raised to power minus 19. For a neutral body has equal number of protons or positive charges and negative charges, right? And a deficit of negative charge would lead to what? A positively charged body. But excess of electrons in an uncharged body or a neutral body would lead to production of what? A negatively charged body. You understand better when we go into more details. So protons are deeply bound within the atom. Electrons are located peripherally. That's why electrons are usually involved in the transfer of charges, not protons, because protons are bound deeply to the nucleus. So what are some materials in electricity? Conductors, they are materials that allow electricity to pass through them. Insulators, they prevent electricity from passing through them. Examples of conductors include metals, graphite as opposed to diamond, which is an insulator. Graphite is a conductor. Acids and electrolytes, they are conductors. The earth is even a conductor. The human body is also a conductor. Insulators include things like rubber, plastic, paper, dry wood, and the likes. Pure water I'm not talking about sachet water, I'm talking about pure water. Distilled water is an insulator. Production of electric charges. So when I was talking about uncharged body, upsetting the balance of charges in an uncharged body will produce a charge on that body. By friction, rubbing transferring charges, creating charge by rubbing one body against another body. So for example, if you rub a glass rod against a material like silk, this glass rod is going to lose electrons to the silk. Since it's losing electrons, there are more positive charges left, right? There are more protons, so it's going to attain a positive charge, and that's one way we can produce a positive charge. Now the silk itself has an excess of electrons now, therefore it will be what? Negatively charged. But conventionally, we always make reference to the rod being used. Now to produce a negative charge, rub ebonite rod with FUR. So rubbing ebonite rod with FUR, electrons are scraped off the FUR. So there's a deficit of electrons in the FUR, so it will attain in what? Net positive charge. While the ebonite rod now has excess electrons, which it's rubbed off from the FUR, and it's going to have what? a net negative charge. So that's how we produce a negatively charged body on an ebonite rod, and then positive charge is produced with glass rod and silk. Electrostatic induction is a method which we use to produce charges where the charge is induced without actual contact. So the bodies do not touch each other. For this case, friction, we rubbed one body over the other one. Even by charging by contact, so is two bodies have to come into contact. But by electrostatic induction, the two bodies don't necessarily have to come into contact. So for example, a positively charged body can come just close to an uncharged body, and it will cause what we call ionization. Ionization is where molecules split into positive and negative ions. So because positive repels positive, negative repels negative, right? But positive would attract positive, will attract what? The opposite charge. So positive and negative attract. That's why the positively charged body brought close to an uncharged body will attract negative charges to this end and repel positive charges to the other end, allowing these protons to leave the body. We're going to be left with what? A net negative charge on this uncharged body. So we have successfully charged this neutral body by electrostatic induction. Same thing with negative, bringing a negatively charged body to a neutral body. Same thing happens. Negative will attract positive charges. Negative charges will be repelled to the end. Connect Earth, and those excess electrons, those electrons will flow out, and we're left with what? A net positive charge on that body. Charge devices. So gold leaf electroscope detects and identifies a charge. So with a gold leaf electroscope, we can tell if the charge is positive or it is negative, or if there's even presence of a charge at all. Gold leaf electroscope looks something like this. If you have seen this device before, with an insulative cork or cover, and then suspended gold leaf. This is a conductor. These are the gold leaves. That's why it's called a gold leaf electroscope. So if you bring a positive charge body close to it, it's going to repel positive charges to the gold leaf. And because like charges repel like charges, the two gold leaf will repel each other because they are both positively charged, right? And we say it has been what? Deflected. So deflection of gold leaf represents what? Presence of charge, right? So when we bring a charge body close to it, there will always be deflection. If we had brought a negative charge close to the gold leaf electroscope, there will be what? Deflection, because negative charges will flow here and what cause deflection of the leaf, because like charges repel like charges. And also this positive charge that we have brought close here will attract negative charge to the end of the gold leaf, that is through the conductor to the coil. Now we can earth it and allow electrons to flow out, leaving a net positive charge on the gold leaf electroscope. In this state, we can say that this gold leaf electroscope is positively charged. So how can we charge a gold leaf electroscope positively? By bringing a positive charge close to the gold leaf electroscope, earthing it, allowing electrons to flow out, net positive charge will be left on the gold leaf electroscope. And now, if we have a positively charged gold leaf electroscope and we bring a negatively charged rod close to it, we have removed this rod, we have removed the earth. Now we bring a negatively charged rod to a positively charged gold leaf electroscope. What do you think is going to happen? So first of all, oh my god, this my diagram is so horrible. First of all, bringing a negatively charged rod to the gold leaf. Let's say we brought it close to this one, and this, I've already removed this, we removed the earthing. Okay, so we brought the negative charge to this. What is going to happen? First of all, it's going to attract the unlike charge. So negative will attract positive. That means all the protons, all the positive charges will flow out of the gold leaf, causing the gold leaf to what? To collapse. Now the gold leaf will be like this. So it has collapsed. That's the effect. So we can rightly identify that it was a negative charge that was brought close to it. That's where we say identify a charge. I cannot go into much detail now because the scope of this video is calculations. You can refer to your textbook for more info on this. Now, Electrophorus, a device that stores and transfers charges. Note the difference. Is that device that looks like this, an insulator handle with a metallic plate and a dielectric base or an insulator base. So this device stores charges and can what? Transfer charges, as opposed to a proof plane. A proof plane looks something like this. So a proof plane only transfers or isolates small amount of charge for sampling or testing. Now, distribution of charges on conductors. Shapes of conductors. We can have cornered conductors like a rectangular conductor. The distribution is fairly even on the smooth or straight surfaces, but on the vertices or on the corners, at the corners, there's a high density of charges that accumulate at those pointy areas. Same thing as the proof plane. The proof plane has a higher density of charges at the tip, but a sparse or low density at the wider side. But for a round conductor would have an even number of charges dispersed around it because it is evenly, there's no edge, there's no pointy area. So that's where we come to point conductors. Point conductors, like we said, has high charge density, and that's why point conductors are used in lightning conductors. They are used as lightning conductors. Why? Because a high density of charges are packed at the pointy region, so causing the air molecules around the conductor to be ionized. Now, electrons will also be attracted. Since these are positive charges, electrons will be attracted to it, and this will provide a path for the lightning to strike. And so from this lightning conductor, it will be conducted to the earth, thereby protecting the house appliances and from electrocution, right? So that's that. Electric fields. Positive charge flows outwards. Negative charge flows inwards. That is the field. The field on a negative point charge flows inwards. The field on a positive point charge flows outwards. That's the difference between positive and negative fields. Now, interaction between fields. So if we have a positive point charge and a negative point charge, the field lines will look something like this. First of all, it will be a force of attraction, and the field lines will look something like this. The arrow will go in this direction because positive flows outwards while inwards is for negative, right? So this will be the direction. Now, Jamb might just label something like this: identify charge A and identify charge B. You just know that charge A is positive. Why? Because flowing outwards, right? Charge B is what? Negative, because flowing inwards. The fields are flowing inwards. Now, for two like charges, it could be positive, it could be negative. The field lines around them, they look like this. Oh, my drawing is so horrible. Okay, the field lines look something like this. Now, what will tell you if it is a positive, if both of them are positive or negative charges, is the direction of flow of the field. Remember, positive moves outwards. So if you see a question where all the arrows are facing outwards, then it's what? These two are positive charges. And this point is always called what? The neutral point. Neutral point as a result of what? Repellation between the two charges. Common unit prefixes used in Jamb questions, Jamb, eᵣε₀A, etc. We have pico, we have nano, micro, milli, centi, deci. Deca is not so popular, so we can even strike this out. Hecto is not so popular, but if you want to learn it, you can still learn it. Now, we're going from smallest to largest. Mega. There are other units too, but these are the most common. Okay, so in a topic like capacitor in electricity, you may have seen a unit called microfarad. This is not the unit, so the actual unit is farad. Micro here, which corresponds to this, is a prefix. That means if you are given something like 5 microfarad, to convert to farad, how do you do that? In place of the micro, you put what? You put 10 raised to the power minus 6. So to convert 5 microfarad to farad is going to be equivalent to what? 10 raised to the power minus 6 farad. And that's how to convert. You can also be given picofarad. Jamb likes to do this thing a lot. You can see something like picofarad. You can see something like nanofarad and the rest. So please know this. There's an easy way to remember. 12, 9. Subtract 3 from 12, you have 9. Subtract 3 from 9, you get 6. Subtract 3 from 6, you get 3. So that's the trend until it gets to centi. Centi is 10 raised to the power minus 2. Remember to convert from cm. For example, you want to convert 100 cm to meters. You divide by 100, right? Divide by 100. What does that mean, actually? It means it's still the same as saying 1 multiplied by time 1 over 100. What is 1 over 100? 1 over 100 is 0.01. 0.01 is what? 0.01 is 10 raised to the power minus 2. So actually, converting from cm to meter is just replacing the centi with 10 raised to the power minus 2. And then you get what? Your answer in meter. So this will give you what? 1 meter. That's the concept. I hope you understand. Force between charges proportional to product of charges. Force between charges is proportional to product of charges and inversely proportional to the distance squared. This is Coulomb's law as in the simplest form possible. Just remember this. The force is directly proportional to the product of two charges, right? And then it is inversely proportional to the square of the distance between those two charges. That is Coulomb's law in a nutshell. So if you have 2-point charges Q1 and Q2, the distance between them, we call it r, right? And then the force could actually be a force of attraction where if they are unlike charges, or repellation if they are like charges. But when you compare it to Newton's gravitational law, you know there's a similar formula. But let's write the formula for Coulomb's law first. So as you can see, the formula here, F is equals to what? K Q1, product of the charges all over square of the distance between them, where K is a constant of proportionality, and the value for K is 9 times 10 raised to the power 9, or 1 all over 4 pi epsilon naught. So another formula we can write out based on the value for K is what? Q1 times Q2 all over 4 pi epsilon naught rho squared. So this is another formula we can use to find force of attraction or repellation between 2-point charges. But when we talk of gravitational law, when we have two masses, for example m1 and m2, you know the formula is similar, but instead it's gravitational constant m1 m2 all over the square of the distance between them, right? So you see how Newton's gravitational law is similar to Coulomb's law. But the difference now is that masses are involved instead of charges, and It is a force of attraction only. Attraction only. Why for Coulomb's law, it could be a force of attraction or a force of repellation, depending on the type of charge. So let's solve this question. Two identical charges situated 2 cm apart. Now they said the charges are identical, so I can just call them, I can just give them the same value, right? Situated 20 cm apart. So the distance between these two charges are what? 20 cm with a force of, okay, so the force of, not tell us what the charge, whether it's positive or negative. So let's just say the force is 1 Newton. We don't know if it's of attraction or repellation, but that does not really matter actually, because we can still use the formula regardless. So let's write our Coulomb's formula. It's given by K times Q1 Q2 over R square, right? They're asking us to find what? Calculate the value of each of the charges. So to calculate the value of each of the charges, you just have to substitute into the formula and make Q subject of formula. So K Q square, remember Q1 is Q, Q2 is also Q. So Q times Q is going to give us what? Q square all over R square. So we can cross multiply, so have FR squared all over what? Divide both sides by K. All over K is going to be equals to what? Q square. Q square is alone. Now, so we can substitute our parameters. In place of F, I'm going to write what? Our value for force, which is 1 Newton. So 1 Newton times R square. What is the distance? 20 cm. Remember to always check the consistency of your units. This is how I do it. Now I'm going to check every other formula. 20 cm is not in SI units, first of all, but okay, let's check the constant. It is in meters. If our constant was given in centimeter square, for example, we could use this like that. But since this is in meters, we have to make sure our distance is also in meters. So to convert to meters, we will divide by 100 or multiply by 10 raised to the power minus 2. Anyone works. So it's going to give us what? 0.2, right? So we substitute. In place of R square, we are going to write what? 0.2 in bracket squared all over, the value for K is what? 9 times 10 raised to the power 9. And so this is equal to Q squared. So let's simplify. 0.2 square is 0.02. So times 0.02. How do I know that 0.2 square is 0.02? Now, one way, you can just press it to your calculator. Say 0.02, I mean 0.02 times 0.2. And your Jamb calculator will give you 0.04, sorry. That was an oversight. 0.04. You can just press that to your calculator. Or another way to just go about it is, 0.2 is the same thing as saying 2 times 10 raised to the power minus 1. So if you square this, 2 squared is going to be what? 4 times what? 10. 2 times 1 is what? 2. It's going to give what? 10 raised to the power minus 2. And this is the same thing as saying what? 0.04. Okay, so over 9 times 10 raised to the power 9. So how do we simplify this? Okay, you convert to standard form. 1 times 0.04. 0.04, remember, is the same thing as 4 times 10 raised to the power minus 2. All over 9 times 10 raised to the power 9. So we're getting closer and closer to our answer. If you bring this to the top, now I'm teaching you how to solve without calculator because there's no raised to power in Jamb calculator. So we're going to have Q square is equals to 4 times 10. Bringing it to the top, we're going to use minus 9 in brackets with this 10. That's just the hack. So it will be minus 2. Bringing 10 raised to power 9 to the top becomes 10 raised to power minus 9. So simplify plus, it's going to be plus, that's normal indices, plus minus 9. That is minus 2 minus 9. That's going to give you minus 11. You can press your calculator to confirm. Minus 2 minus 9 is minus 11. All over what? All over, we still have 9 at the bottom because we only moved 10 raised to power 9 to the top. So this is going to end up as what? 4 over 9 times what? 10 raised to power minus 11. But we still have square here, and we're asked to calculate the value of each charge. So how do we calculate the value of Q? Now, one way is to just take the square root. That is, if square root is not in your Jamb calculator, this is the way you can go about it. Take the square root of both sides, right? Your Q is standalone. Take the square root of this, and you are going to be left with. So this square root you have to take the square root of every single term here. So square root of 4 is 2. Square root of 9, so over 3, times what? We don't know what the square root of 11, 10 raised to power minus 11 is. So there's a hack we do. We can split it, 10 raised to power minus 1 times 10 raised to power minus 10. You know, according to indices, this is the same thing as saying 10 raised to power bracket minus 1 plus bracket minus 10, right? So this will give you minus 10 raised to power minus 11. So it's still the same thing, right? But now we're taking the square root of this instead. So taking the square root of this, and also another thing you should note is, this is mathematics, just basic maths. X squared, square root of x is the same thing as saying x raised to power half. Square root means raised to power half. So it just tells us that square root of 10 raised to power minus 1 times square root of 10 raised to power minus 10 is the same thing as saying is the same thing as saying 10 raised to power 10 raised to power half. So half times 10 is going to give us 10 raised to power minus 5, right? But this we still don't know the value. But one thing we know is that 10 raised to power minus 1 is the same thing as 1 over 10. And 1 over 10, square root of 1 is 1, right? And then square root of 10, we don't know what the square root of 10 is, but we are closer to our answer. So this is what I arrived at after simplifying 10 raised to power. So we need to figure out what root 10 is. Now there's a simple hack for this. Root 10, you find the closest root, the closest perfect square to 10. What's the closest one? Is 9. I know that the square root of 9, the square root of 9 is 3, right? So that just means that if we multiply 3 by 3, we're going to get 9. So we have to multiply 3 point something to get 10. So I'm just going to take a guess, 3.2 times, or 3.1 times 3.1. This is just a guess. I've never used my calculator. So if I press that 3.1 times 3.1, I got 9.61. That is close. That is close to 10. So maybe I can even work with 3.2 times 3.2. So 3.2 is my closest guess. So in place of root 10, I'm going to write 3.2 as the square root of 10. Now, assuming there is no square root in your calculator, but if there's square root, just take the square root and get done with your solving. So 3 times 3.2 is equals to 9.6, right? So we have 9.6 at the bottom. 2 divided 9.6 is what? Is 0.21 approximately. So everything here simplified would give us, let me create space, would give us 0.21 approximately. So Q is equals to 0. So Q is equals to 0.221 times what? Times 10 raised to the power minus 5. Now convert this to standard form. Move the decimal place once. Move the decimal place once. It just means you should, this place will become 10 raised to the power minus 6. So 2.1 times 10 raised to the power minus 6. Our options, I can already see my answer here as A. Our answer is in microcoulombs, but we calculated using SI units, right? That's why we got our answer in coulombs. So to convert 2.1 times 10 to the power minus 6 to microcoulombs, 10 to the power minus 6 is micro, if you remember our units. So in place of 10 to the power minus 6, we have micro, and we got the exact answer. Electric field intensity. What's electric field intensity? Electric field intensity is the force per unit charge. The formula is force over charge. Just remember that. The units include Newton per Coulomb or volts per meter. The reason for this other units is because there's another formula for electric field intensity. Electric field intensity, apart from it being the force per unit charge, we can replace force here with, first of all, we know that, let me see if I can derive it. We know that work done is equals to QV. We know that potential difference is equals to work done over charge. Sorry about that. We know that potential difference is equals to work done over charge, right? Therefore, work is equals to QV. I was correct. Then, in place of work done, we know that work done is force times distance, right? So force times distance in place of work done is equals to QV. Make force subject of formula. We're going to have what? F is equals to QV. Divide both sides by D is what? QV over D in place of force. So we bring back our electric field intensity formula, which is what? E is equals to force per unit charge. Therefore, since force is QV over D, we can write what? QV over D in place of force. Divide charge. Charge cancels charge. We're left with what? A new formula. Voltage over distance. So that's why we have another formula for electric field intensity. So you can either use this, depending on your question, you can either use E equals V over D, or use E is equals to F force per unit charge. That's electric field intensity. Now, in terms of permittivity of free space, that is epsilon naught, there is a formula we can also derive. Remember, Coulomb's law states that force is equals to constant, okay, the one you know, constant proportionality times what? Product of two charges over square of the distance between them. But force in Coulomb's law is also equals to what? Q1 Q2 over 4 pi epsilon naught r square. Because what? Because K, the value for K is 1 over 4 pi epsilon naught, which is equal to 9 times 10 raised to the power 9. So knowing this, we can derive a formula for electric field intensity from this value of force, just the same way we derived a new formula for electric field intensity using work done. Okay, so let's go about it. So in place of force, we are going to put this value for force. But the thing is, electric field intensity in this case will be the field intensity of a test charge, right? So let's say this is a charge. Let's say maybe, for example, we have a positive charge. Let's say we have a charge Q, right? Putting a test charge close to it to calculate what? The field intensity. So let's call the test charge Q. The distance r, and then what? We want to calculate the force per unit charge that this test charge is exerting on this charge. So in place of F, we're going to put this formula. I'm just showing you derivation. So Q1 is going to be Q, Q2 is going to be small letter q, right? So we're going to write that Q times Q, that is Q1 times Q2, all over 4 pi epsilon naught r squared. Remember, this is just for F. Divide. So we're going to write the division sign. Divide what? Q. We find out that what? Once again, Q cancels out. Q cancels out, and we're left with what? We're left with a new formula for electric field intensity. E is equals to Q over 4 pi epsilon naught r squared. So this is another formula for electric field intensity. Take note. How many formulas have we derived here? This is 1, the main formula. This is another one we derived, 2, and this is what? Formula 3. So if you don't know the derivation, you can just cram. But it's best you know how to derive it. So let's take a look at this question. A charge of 2 times 10 to the power minus 5 coulombs, not microcoulombs, experiences a force of 18 Newton in a uniform electric field. Calculate the magnitude of the electric field intensity. So as easy as that, electric field intensity is equals what? Force per unit charge. What's the force given? Force is 18 Newton. What is the charge? The charge is 2 times 10 to the power minus 5. Simplify. 80 divided by 2 is 40. We have 40 over 10 to the power minus 5 left. Okay, we can have 1 here. 1 times 10 to the power minus 5 is the same thing actually. Bring this over. We're going to have what? 40 times 10 raised to the power 5. The sign changes to positive, just so you know. Okay, at the end of the day, we're going to be left with what? 4 times 40 times this is the same thing as saying 4 times 10. 4 times 10 is 40, right? Times 10 to the power 5. 10 to the power 1. 1 plus 5. That's how we got what? 4 times 10 raised to the power 6. What's our unit? Newton per coulombs. That is unit for electric field intensity. So B is the correct answer. Next question. An oil drop carrying a charge of 1 times 10 raised to the power minus 19 coulomb is found to remain at rest in a uniform electric field of intensity. Calculate the weight of the oil drop. Okay, so this is a special case. We're talking about weight of the oil drop. First of all, let's derive something. This is how you think logically in physics. ask yourself, they're asking us to calculate for weight. What is a formula that I know in weight? I know that weight is equals to mg, right? I know that weight is equals to mg. And I know a formula for electric field intensity. Actually, they say we should calculate the weight of the oil drop. I think the question was calculate the mass of the oil drop, not weight. Sorry. Weight is the same thing as force, though. So our formula for electric field intensity, we can write that out. E is equals to F per unit charge, right? And just substitute our value for electric field intensity is equals to force. Force is the same thing as weight. They have the same units. So in place of force, we can just write weight there. All over the charge. The charge is what? 1 times 10 to the power minus 19. Cross multiply, weight is going to be what? 1200 times 10 to the power minus 19. Take this, convert to standard form. I have to take decimal points. 1, 2, 3. So I have 1.2. Since we counted 3 to the left, so I was supposed to what? I was supposed to subtract, like reduce 19 by 3. So 19 minus 3 is what? 19 minus 3 is 16. So 10 to the power minus 16 Newton. This is the value for the weight. Now, if they had asked us to calculate the mass, we can use actual gravity to calculate for the mass of the oil drop. Question 4. The potential difference across a parallel plate capacitor is 10 to the power 3 volts. Okay, so we already got voltage, right? Is equals to what? 10 raised to the power 3. If the distance between the two plates is 10 cm, so we also got distance 10 cm. Calculate the magnitude of the electric field strength. Now, remember, electric field strength is the same thing as electric field intensity. And we derive the formula E equals V over D. So voltage, you can just divide it by what? The distance. Remember to convert to SI unit. 10 cm to SI unit is what? Divide by 100, you get 0.1 meter. So substitute our formula, 10 raised to the power 3 over 0.1 meter. How do we simplify? 0.1 is equal to 1 times 10 raised to the power minus 1, right? Take this up, I'm going to get 10 times 10 raised to the power 1. 10 times 10 raised to the power 3 is 10 raised to the power 4. So electric field intensity is going to be equal to what? 10 raised to the power 4 volts per meter. Where's our answer? A is the correct answer. 10 raised to the power 4 is same as 1 times 10 raised to the power 4. Then electric field flux. Electric field flux is a product of field strength and perpendicular area. So you multiply electric field intensity by area, you get electric field flux. So any question we have solved on electric field intensity now, they could give you the area of surface and tell you to calculate for the electric field flux. All you have to do is multiply the electric field intensity by that area. As simple as that. For a sphere, please note that the electric field flux is equal to what? Charge all over permittivity. Epsilon naught means what? Permittivity of air or free space. So that's what electric field flux. Electric potential. Electric potential is I would say is a fancy name for voltage. Just like, if you remember, gravitational potential. Was it gravitational potential? Sorry. Just like, if I remember correctly, gravitational potential, gravitational field strength remember the formula was force per unit mass. So gravitational field strength is given as what? Force per unit mass. That was a fancy name for acceleration to gravity when we did Newton's gravitational law. Same thing as this one. Physics is quite funny. In this case, the formula V is equals to work over charge. Electric potential is the same formula for voltage or EMF, work done in an electric circuit. So just remember that. Remember this formula. Now, another formula is Q all over 4 pi epsilon times distance. How do we arrive at this formula? Now, you might be interested to know that work done is force times distance. You know that already, actually. So it is safe to say that the potential is equals to, electric potential is equals to what? Force times distance per unit over charge, right? But force has a value. Remember that force, we established the fact that force Q1 over Q2, Q1 times Q2 all over what? All over 4 pi epsilon naught r squared, right? This is Coulomb's law. From Coulomb's law, we can substitute this, but the catch is we have to make one of the charge the same. So in place of force, I'm going to write what? Q times what? Q. So one of the charges are the same. Times what? Actually, we need to complete it first. So all over what? So all over what? Okay, this is my functioning. Okay, Q times Q all over 4 pi epsilon naught times r squared. Now they use d here. D is same as distance. R is also distance, so we can still use d squared, right? Times what? Times d as well, all over charge. So you find out that d here, we have 1 and we have 1d left here. Charge cancels out charge, and then you get this formula, Q over 4 pi epsilon naught times d. So this is another formula for electric potential. Okay, so let's work on this question. Calculate the potential at a point 30 cm from a charge of 1.5 times 10 raised to the power minus 5 coulombs. Now, most persons would not know what to do here, because the formula they know for potential is V is equals to work done over charge, right? But now they're giving you distance. They're giving you distance and they're giving you a charge. What are you supposed to do with? Where are you supposed to get force from? So most persons will be stuck here, but we do have another formula, right? This. So there's also distance, and we have 4 pi epsilon naught. Therefore, we can use that formula. So applying that formula for electric potential, Q over 4 pi epsilon naught times D, we can substitute the charge, value for charge, 10 to the power 5, over what? 4 pi epsilon naught. Now here's the thing. The value for 1 over 4 pi epsilon naught is equals to 9 times 10 raised to power 9. Do not ever make the mistake of going to put 9 times 10 raised to power 9 at the bottom here. Don't make that mistake, because 1 over this is equals to this. Therefore, 4 pi epsilon naught is going to be equals to what? 1 all over 9 times 10 raised to power 9. So if you put 1 all over 10 raised to power 9, in fact, let me just do it so you see what I'm talking about. In place of 4 pi epsilon naught, let's put this. You see what happened? This is the same thing as saying Q, what is this? Divide 1 over 9 times 10 raised to power 9. You have to invert in division, right? And change to multiplication. Do you see that? So that value has to be at the top actually. So times 9 times 10 raised to power 9. Please don't make that mistake. I made that mistake once during my exam. It was after coming out from the exam hall that I realized the horrible mistake I've made. Remember, I've already substituted the value for 4 pi e naught, so this is already out. What's left at the bottom is what? Distance. And distance is what? 30 cm. Convert 30 cm to meters. We have what? 0.3. So 0.3. From here we can simplify. 1.5 divided 0.3 is what? That should give us 5. So it's 5 on the dot. 5 times 10. Okay, let's bring this 9 first. 5 times 9 times 10 raised to power minus 5. Always collect like terms. Put the exponent on one side, put the whole values on one side. So 5 times 9 is what? 5 times 9 is going to give us 45, right? So 45 times 10 raised to power minus 5 times 10 raised to power 9. How do we go about it? We use what? Plus, because this is multiplication. If it's division, we'll use minus, Abi. But this is multiplication. So we'll say minus 5 plus 9. Minus 5 plus 9 is same thing as saying 9 minus 5. 9 minus 5 is what? 10 raised to power 4. So 4.45 times 10 raised to power 4 to standard form. We still have to move this decimal backwards. And moving decimal backwards, this number will have to increase. So our final answer for the potential is 4.5 times 10 raised to power 5, and that's our answer. Joule per coulombs. That is unit for electric potential. Okay, question 6. A point charge of magnitude 2.5 microcoulomb is moved through a distance of 0.04 meter. Calculate what? Calculate work done on the charge. Okay, this one we can just use our normal formula for electric potential. That is work done over charge. They're asking us to calculate the work done on the charge. So cross multiply work done is equal to QV. So just have to multiply Q times V. So the charge is 2.5 microcoulombs. 2.5. In place of micro, we put what? 10 raised to the power minus 6, because that's the value for micro. So times 10 raised to the power minus 6 coulombs times what? Times the voltage. Do I have voltage here? Wait, move through a distance of, so this volts per meter, this is electric field intensity, right? Okay, this question is a little bit technical. Against a uniform electric field of intensity, they give us 15 as our value for E. Okay, so how will I go about this? First of all, we're given electric field intensity. I know a formula for electric field intensity is equals to force over charge. We can start from there. Okay, so from here I can get force. This is a very technical question. So we are going to use electric field intensity first. So 15 is equals to what? Force. We're not given force. Let's just calculate for force. But we have charge, right? So we can use the charge, 2.5 coulombs. 2.5 times 10 raised to the power minus 6. We can use that to get the force. So the force is what? 15 times 2.5 times 10 raised to the power minus 6. Now that I've gotten force, we can calculate work done. How do we calculate work done? We know that work done is equals to force times distance, right? So we just need, what are we looking for now? We just need distance to get our work done. That's how you think logically. So we're looking for distance now. So how do we get distance? First, let me wipe all this rubbish I just wrote here. So distance, we can use another formula for electric field intensity, which is E is equals to V over D. And since we have potential, we have electric field. What am I doing to start with? So we can get distance from here, right? No. We also know that V is equals to work done over charge. So from, and they're asking us to calculate work done. We can't get distance from here either. So we have field intensity as 15. That's why it's good to write out your parameters first before solving. I just got confused. Electric field intensity 15. Charge is what? 2.5 microcoulombs. Distance, we're given distance as 0.04. Can you imagine? Can you imagine the distance we're looking for? 0.04 was looking at us there, because work done is force times distance. So 0.04, the work done on the charge is equals to what? Force times distance. And we already got our value for force, so we multiply by what? The value for distance. And so if I simplify, 15 times, you can just press that on your calculator, sure. 15 times 0.04, you have 0.6. So 0.6 times, oh, there's also 2.5. 0.6 times 2.5, you are left with 1.5. So 1.5 times, the only two I have left is 10 raised to the power minus 6 joules. That is the value for energy. I hope you understand what I did. If you are confused, let me clear the air. First of all, you write out your parameters. Q is 2.5 microcoulombs. Distance is 0.04 meters. And then electric field intensity was given as 15 volts per meters. right? Now we're asked to calculate what is the work done, and we know that work done is equals to force times distance. Okay, so with this in mind, that work done is force times distance, we know we just have to find force and multiply it by the distance which was given. That means we can apply our formula for electric field intensity, which is, remember electric field intensity, we have two formulas, either force per unit charge, or we have what E is equals to over D. So which one is the best formula to use here? So we're given E, we're given Q, we can find force. So this is the best formula. So substituting, we now got what? Substituting the value for electric field intensity, which is E, that is 15, is equals to force, which we are looking for, all over charge, 2.5. So cross multiply. After getting the force, we multiplied it by this distance. Charge on capacitors. A capacitor, device with metal plate separated some distance d by an insulator. Insulator is also called dielectric for storing electric charges. So this is the image, as you can see here, two metal plates which are separated by some distance, as you can see, separated by distance, and it's used for storing electric charges, as opposed to an electrophorus, which both stores and transfers electric charges. Formula is given as Q equals to capacitance times voltage. Q means charge, C means capacitance, V means what? Potential difference or voltage. They are the same thing. This is a picture of a real life capacitor. You can see the two metal plates with the distance between them. Okay, capacitance of a capacitor. So what is capacitance? The ability of a capacitor to store electric charges, to store small electric charges. That is capacitance. Formula is given as C is equals to Q over V. From our formula for charge here, make C the subject formula, divide both sides by V. You are going to get what? C equals what? Q over V, as we can see here. Other formulas include C is equals to permittivity of the dielectric times area all over D. This one, C is equals to permittivity of free space. That is, if the permittivity of dielectric is equal to permittivity of free space, times area all over D. So relative permittivity is also called what? Dielectric constant. And dielectric constant is equals to the ratio of permittivity of dielectric to what? Permittivity of free space, air or vacuum. It could be air, it could be vacuum. Therefore, permittivity of the dielectric is equal to the product of relative permittivity, and that name for relative permittivity is dielectric constant, times what? Times permittivity of free space. So we have a main formula for capacitance which goes as follows: C is equals to epsilon r, that's the relative permittivity times what? Permittivity of free space times area all over D. This is the main formula for capacitance. Now this formula tells me a lot of things. It tells me, number one, that capacitance is directly proportional to area, which means if we increase the area of the plates, increasing the area of the plates would increase the capacitance. That is the meaning of directly proportional. Now, D, which is at the bottom, capacitance is inversely proportional to the distance between the plates. So if you increase the distance between the plates, you actually what? Decreasing the capacitance of the capacitor. That is what we mean by inversely proportional. So take note of that. The capacitance of a capacitor depends on both the area and the distance between the plates. A parallel plate capacitor consists of two plates each of area. So they give us the area of the plate separated by a dielectric of thickness and dielectric constant. Calculate the capacitance of the capacitor. So we just have to write down our formula. What is the formula for capacitance of a capacitor? C is equals to what? Relative dielectric or relative permittivity, or what? Dielectric constant, epsilon r, what? Times permittivity of free space times area all over what? Distance. So that's what we need to do. So we have dielectric constant, which is relative, is the same thing as relative permittivity. So in place of epsilon r, we'll put 900 times what? Permittivity of free space, which is E naught, epsilon naught, is 8.85 times 10 raised to power minus 12 farad per meters. Okay, times what? Area. What is the area? The area is 9.6 times 10 raised to power minus 3 meters square, all over what? The distance. What is the distance between the plates? The distance, okay, take note, distance is also called thickness. The distance between the plates is also called the thickness of the dielectric. So that is one way to know it. 2.25. Come on. If this is metal plate, you have an insulator material between them, right? This is the dielectric. This is the distance between the two metal plates. How thick this dielectric is would determine the distance between the plates. So they are actually the same thing. That's what I meant. So now we have to simplify and we get our capacitance. Is there any unit we did not convert? Everything is the SI unit. These people decided not to be wicked this time. So 2.25 times 10 raised to the power minus 4. The way I like to solve quickly, let me teach you a hack. So first of all, just multiply all the whole. Multiply 900 by 9.6. You can solve along. 900 times 9.6 is 8640, right? Times, oh, I missed this, 8.85 times 8.85 is what? 7. It is 76464. So I left with what? 10 raised to power minus 12 and 10 times 10 raised to power minus 3. Always put the 10 raised to power together because Jamb calculator does not have raised to power. All over what? 2.25 times 10 raised to power minus 4. Now 76464 divided by 2.25 rather. We have what? 33984 times 10 raised to power 12 times 10 raised to power minus 3. We still have all over 10 raised to power minus 4 here. Okay, now move the decimal place 1 2, 3, 4. So you are going to be left with approximately 3.4. And we move the decimal place how many places? 4 places, right? So I have to multiply by what? 10 raised to power 4 times what? 10 raised to power minus 12 times 10 raised to power minus 3. We still have all over 10 raised to power minus 4. Don't forget that. Now we are about to get our final answer. So our final answer is 3.4 times 10 raised to power 4. There's multiplication here. So when you see multiplication, just add the exponent. So 4 plus what? Brackets minus 12 plus what? What's the next thing? Plus brackets minus 3. Then there's one under. Whenever I see division, use what? Minus. So what? Minus what? Minus brackets minus 4. Close the brackets. So our final answer is going to be 10 raised to power what? So the reason why this is in brackets is because you have to treat them delicately. Negative times negative will give you positive. So we have plus 4 here already. So we have plus 4. So 4 plus 4 is 8, right? So 8 minus 12 minus 3 is what? We are still going to get a negative answer. 8 minus 12 minus 3 is minus 7. So our final answer is 10 raised to the power minus 7, whatever the unit for capacitance is. What is the unit of capacitance? Farads. Okay, next question. Capacitance of an isolated sphere is given by this. Just note the formula. Don't want to go into too much detail. Energy stored in a capacitor is given by 3 formulas. 1/2 times charge times voltage, 1/2 times capacitance times voltage squared, or Q squared, that is charge squared, all over 2 times the capacitance. These 3 formulas are important, and Jamb loves bringing questions for energy stored in a capacitor. So please take note of these formulas. Now we have a question 8. The energy stored in a capacitor of capacitance 5 microfarad. So we're given capacitance as 5 microfarad, and we're given the energy stored. So the work done, or the energy stored, is 40 joules. What is the voltage applied across its terminals? So we're looking for what? We're looking for voltage. Which formula relates C and voltage? If I remember very well, I remember that 1/2 QV. Okay, that does not work. 1/2 CV square. So it's W equals 1/2 CV square. So we have capacitance and we have what? We are looking for voltage, but we have what? Work done. So in place of work done, put your 40 joules. 1/2 times, you don't just put 5 there. You have to convert to micro. You have to convert from microfarad to farad. So in place of micro, you put 10 raised to the power minus 6. Okay, I have to write the 5 first. So 5 times 10 raised to the power minus 6, we have converted what? Times voltage squared. So voltage squared is equals to, so how do we simplify this easily? Well, first of all, we can just say 5 times half is 2.5, right? So 40 here all over, divide both sides by 2.5 times 10 raised to the power minus 6. Okay, so let's simplify. We have another square case. Let's hope this will be easy to simplify. So 40 divided by 2.5 is 16. This one is easy. Thank the stars. These are the kind of easy questions, easy ones Jamb will give, because there is no square root. There's no square root in Jamb calculator. So you have to make do with what you have. So 40 divided 2.5, we have 16, thank God, all over what? 10 raised to power minus 6 left. So already I can already see my answer. I don't know if you can. Let's simplify further here. So you have to take the square root of both sides, right? So remove the square. To remove the square, so therefore v is equals to square root of 16 all over square root of 10 raised to power minus 6. Square root of 16 is what? Square root of 16 is 4. Square root of 10 raised to power minus 6 is what? Remember when I told you that x raised to power half is the same thing as saying square root of x. Therefore, square root of 10 raised to power minus 6 is the same thing as saying 10 raised to power minus 6 raised to power half. So half of 6 is 3, so we have 10 raised to power minus 3. Bring this to the top. We have v is equals to 4 times 10. Remove the negative sign when you bring to the top, or rather you change the sign. If it was positive, when it comes to the top, because it becomes what? Positive. So opposite. Positive will change to negative, negative will change to positive. That's what I mean. So 10 raised to power 3. 4 times 10 raised to power 3 is 4,000 volts, and this is our answer. Okay, here are some recap questions for you. If you have been following, you should be able to answer these questions easily. So take a look at the questions, try to attempt them. Try to attempt these questions. They are very easy. And drop your answers in the comment section. Just write recap A, then your number and the option you choose. Okay, current electricity. Current is time rate of flow of electric charge. So before, what we just treated was static electricity. The electrons were not yet mobile. When we have current, it means the electrons are moving. Now there's conventional current, there's conventional flow, and there is electron flow. Conventional flow is from positive to negative, from positive to the negative direction, while electron flow is from negative to positive. Take note of that. Now the formula for current is I is equals to Q over T. That is charge per unit time rate of flow of charge. So Q over T is the formula for current. Potential difference, the work done in moving a unit positive charge from one point to another, measured in volts. Electromotive force is the total work done in driving 1 coulomb of electricity round a circuit. Is also measured in volts. So electromotive force and potential difference, they are almost the same thing. But what is the difference between electromotive force and potential difference? The difference is that electromotive force is the normal value for the battery. Potential difference is the value of voltage at the terminals. You understand better when we treat internal resistance. So formula for electromotive force is also we also did electric potential, where V was W over Q. So this is actually share the same formula. That's why we can use EMF and potential difference interchangeably, because their formulas are similar. Okay, circuits. What is a circuit? A circuit is a path provided for electric charge to flow and do work. it usually comprises of what? A load, number one. The load in this diagram here is the bulb. A conductor, the conductor in this diagram is the wires. And what? An energy source. The energy source is the battery in this diagram. So those are the three main components of a circuit. Now, types of circuits, we have open circuits, we have closed circuits, and we have short circuits. Short circuits, let me start with open circuits. Open circuit is when the path of flow of electricity is cut off. That is, it is open. Let me explain in a simpler way. So you have let me draw a path. So this is the bulb, that's the load. Okay, this thing have symbols. So the symbol for electric bulb, this is the symbol of electric bulb. And then this is the symbol for a switch. And this is our symbol for battery. So an open circuit is one where there is no continuous flow around the circuit and the circuit is not doing work on the load. That is an open circuit. The switch is open in an open circuit. As you can see, current cannot flow because there is a gap here. In a closed circuit, we cannot close the switch. So if I close this switch now, there is continuous flow of current and the energy source is doing work on the load, which is the bulb in this case. That's closed circuit. Then short circuit. What is short circuit? Short circuit is also called bridging. Bridging when the positive and negative terminal are joined together without a load. It's called short circuiting. This is very bad for the battery. It will sometimes when you do it, it can spark and lead to fire hazard. So short circuiting is very, very bad. When there is no load and you join the positive terminal to the negative terminal, you have short circuited that battery. Okay, symbols used in electric circuits. Pause and recap or review. Ohm's law states that the current flowing through a metallic conductor is directly proportional to the potential difference across its end, right? The constant of proportionality is the resistance offered by the conductor. So the formula is given by what? V is equals to IR. The unit of resistance is in ohms. Factors affecting electrical resistance include area or thickness, length, and what? Temperature. These are some examples of factors affecting electrical resistance. What is resistance to start with? Resistance or a resistor restricts the flow of current to an extent. Yeah, it restricts the flow of current. That's why it's called a resistor. So area, how does area affect resistance? Now you can be asking an example question for resistivity. Resistivity is directly proportional to resistance. So the greater the resistance of a capacitor, the greater its resistivity, the ability to resist the flow of current. Let's say we have a 1 ohm resistor and a 5 ohm resistor. Which one will have a higher resistivity? It is the 5 ohm resistor because it has a higher resistance of what? 5 ohms. Now another thing too, area. Area is directly proportional to the resistivity represented by P, which means in a conductor, if you have a thin conductor versus a thicker conductor, which one is going to resist the flow of current more? If we increase the area, resistance is going to what? Resistance is going to increase. Resistivity is going to increase. So the thicker conductor will have a higher resistivity. That's what that means. Then what about length? Length of the conductor. So when we have a conductor, you have a long one and then a short one. Which of these is going to have a higher resistance? We'll go back to our formula. So resistivity is inversely proportional. As you can see, it is inversely proportional to length. That means as length increases, resistivity what? Decreases. What? As length increases, resistivity decreases. Yes, that's for resistivity. But resistance itself, it increases with length. We have to make resistance subject to formula. So when we have RA, that is resistance times area over L is equals to resistivity. Making RO subject to formula, we're going to have what? Resistance is equals to resistivity times length all over what? Area. Therefore, a thicker conductor will have a lower resistance compared to a thinner conductor, and a longer conductor will have a higher resistance compared to what? A shorter conductor. That is why a short charger will conduct electricity better than a longer cord, because as length increases, resistance also increases, directly proportional. Also, as area increases, resistance decreases. Area or thickness. As thickness decreases, resistance increases. So that's the relationship between what? Resistance and area and length. Then what about temperature? Temperature, increasing temperature of a conductor will increase its resistance. Please take note of that. Increasing the temperature of a conductor will increase the resistance. But for semiconductors, it is the opposite. So this is for conductors. For semiconductors, increasing temperature, funny enough, we actually decrease the resistance to flow of electricity. Now, conductivity is the inverse of resistivity. So if resistivity is equals to RA over L, conductivity is going to be equals to the inverse of resistivity, which is what? L all over RA. That means if we increase area, we increase conductivity, or we decrease conductivity. So the thicker a conductor is, always pair it with resistance, please. If they ask you for resistivity, it is different from resistance. Now, although resistivity, as you can see here, is directly proportional to resistance, but one of these can just be considered a constant. Resistivity of a material can be considered a constant because different materials have their own resistivity. So when you want to make comparisons, always use resistance as the subject of formula. So let's solve. This is a question on Ohm's law, or rather variation of resistance with area and length. A wire of cross-sectional area 0.6 millimeters squared. Okay, this case should be very interesting. So the area is given as what? 0.6 millimeters squared. Has a resistivity of what? So let's write the resistivity 7.2 times 10 raised to the power minus 7, and what? Length of what? They said we should calculate the length. Okay, and then calculate the length of the wire that will have a resistance of what? So our R is 3 ohms. Writing our formula, I know resistivity is equals to RA over L, or resistance is equals to PL over A. Neither of them. We just have to make length subject to formula. Or we can just substitute like that. No stress. 0.6 millimeter squared. But your answers are in meters. So you have to convert units. So how do we convert from millimeter squared to meter squared? How do we do that? Okay, first of all, we know that 1 meter is equals to, milli means what? Milli means 10 raised to the power minus 3. 1 meter is equals to 10 raised to the power minus 3 millimeter. Abi? No. 1 millimeter rather is equals to 10. In place of millimeter, we are going to put 10 raised to the power minus 3. So 1 millimeter is equals to 10 raised to the power minus 3 meters. Now, if 1 millimeter is equals to 10 raised to the power minus 3 meters, then how about 1 millimeter squared? So 1 millimeter squared, we're going to square both sides. That's going to give us what? 1 millimeter squared is equals to, because 1 square is 1. 10 raised to the power minus 3 squared, 2 times 3 is 10 raised to the power 6. We're going to have what? 10 raised to the power minus 6 meter squared. Now we can convert 0.6 millimeter squared to meter squared. So 0.6, therefore 0.6 millimeter squared is going to be equals to what? Let's call it x. We can then cross multiply and get our value in meter squared. So x times 1 is x. 0.6 times 10 raised to the power minus 6 is our value for meters. We can convert this to standard form or just leave it like that and use it. So this is our answer in meter square for the value of area. Now we can substitute into our formula. So we're given our resistivity as ohm meter. Okay, that's something you should note. The unit for resistivity is ohm meter. Remember that. Then if the unit for resistivity is ohm meter, what will be the unit for conductivity? Remember that conductivity is the inverse of resistivity, which just tells you that conductivity formula is going to be per ohm per meter, something like that. So what were we? Resistivity is 7.2 times 10 raised to the power minus 7 ohm meter. Resistance, is that what we're looking for? No, we have resistance of 3 ohms times what? Area. What is our area? We converted to what? SI units here. So that is 0.6 times 10 raised to the power minus 6 all over length. We're looking for the length. So cross multiply and we can get the length. So L, you divide both sides by 7.2 times 10 raised to the power minus 7. You have 0.6 times 10 raised to the power 6 all over 7.2 times 10 raised to the power 7, right? Multiply, bring this here. Or an easier way to look at it is just exchange L and this and wherever this. So how do we simplify? From all I've been doing since, you should be able to simplify this. You can pause the video and try to simplify it yourself without using a scientific calculator. Use market woman calculator, the Jamb type calculator that does not have raised to power, square root, or all those other functions. So the way I will go about this is 3 times 0.6 first. I can do that first. I got 1.8. So 1.8 divided 7.2. I got 0.25. So 0.25. 10 raised to the power minus 6 divide 10 raised to the power minus 7. This comes up, becomes plus 7. So 7 minus 6 is what? 1. So 0.25 times 10. And that's going to give us what? 2.5 meters. Now you would notice that if we did not convert our units first, we would have been struggling to choose between A or B. In fact, our answer won't have tallied, but we're able to solve and get the accurate answer. This is how Jamb confuses students. When you don't solve very well, you will not be sure of your answer. Is it 0.25? Some person will rush again and choose 0.25, not knowing that you have to still multiply by 10 to get 2.5 meters. Question 10. If a resistance is halved and halved in value and the PD across it is tripled, then the ratio of the new current to the old one is. Okay, so this is a typical Jamb question. I got this from Jamb past question. So how do we go about this? First step to solving a physics question is to understand it. In your question, you have what? Resistance. You also have what? PD. And you have current. Ask yourself, which formula relates resistance to potential difference and current? It's Ohm's law formula. It's Ohm's law formula. So Ohm's law formula is V is equals to IR. Abi? That's the formula we're going to use. So the resistance is halved. The resistance is halved. So we can say R over 2. And the PD across it is tripled. What is PD? Potential difference or voltage. So the voltage is tripled. So I can say 3V, 3 times V tripled is equals to. Then the ratio of the new current to the old current is what? Okay, so I'm going to call the new current I. Let's just call the new current I2. So now I'm going to make I2 the subject of formula. So I2 is equals to, okay, so 3V, you have to divide both sides by R over 2. So this cancels out, divide R over 2. R over 2. This is the same thing as saying I2 is equals to 3V divided by R over 2, right? Then you invert 3V times 2 over R, so we arrive at 6V over R. This is our value for what? This is our value for I2. Now what about our value for I1? Our value for I1, or the old current, is given as what? We have to change subject of formula here. So change subject of formula, we have I is equals to, divide both sides by R. You have R, so V over R is what we have here. Now this is the formula for the old current. And our question is asking, what is the ratio of the new current to the old one? So this is the new current. So we are going to write the new current ratio the old current, which is V over R. V over R, as you can see, V over R cancels out. And you're left with what? 6:1. So D is the correct answer. Resistors. What are resistors? We already talked a little about resistors. Resistors are devices in circuits that resist the flow of current, as the name implies. So what is the symbol for resistor? If you looked at that drawing, or that list rather, where they mention different devices and their symbols, you find out that the symbol for resistor is either this or this. So this is the symbol for resistor. Not to be confused with, please don't confuse that with this. This one is the symbol for inductor. Okay, so now that we know the symbol for resistor, let's talk about parallel and series resolution for resistors. To resolve resistors in parallel, first of all, what is parallel? Parallel is when you have resistors attached end to end. For example, these two resistors now, as you can see, if you attach their ends, both ends, they are in parallel. It is not the position or the orientation, but both ends that are attached. Okay, and if you have a voltage, a cell here, then this confirms really that they are in parallel. Now what I mean is not the orientation. You can have resistors like this if you feel it is the way they are oriented. You can have resistors like this and still find out that they are in parallel. How? First of all, they have to be connected at both ends. So this is the first connection, this is the first end, and the second end will be like this. So they are connected at what? At both ends. Now, where would the electric source come from? It should come from the point where both ends meet. So these two resistors also are in parallel. These two resistors are in parallel. It is not the arrangement, it's not the arrangement, it is what? The terminal. If both terminals, both ends are joined to one another, then they are in parallel. Take for example, you can have even three resistors. You can even have up to three resistors that are joined at both ends like this. These three resistors are in parallel. So when I'm talking about parallel, what is even series? So series should be only joined at one end. That's what we will tell you resistors are in series. So for example, we can have R1 joined to another resistor, R2 joined to another resistor, R3. For example, these three resistors are in series. So how do we resolve resistors in parallel and resistors in series? To resolve resistors in parallel, we use the formula 1 over the net resistance, that is the total resistance, is equals to 1 over each of the resistors in parallel, R1 plus 1 over R2 plus 1 over R3. That is the formula. That is the general formula. So you can go as far as R100 if there are 100 resistors. While resistors in series, the total or the net resistance is given as R is equals to R1 plus R2 plus R3. Okay, so current and voltage principles. Resistors in series, the same current flows through them. I want you to remember this like the back of your hand. Resistors in series, the same current flows through them. So if we complete this circuit now, you see that the single, if I complete this circuit now, let me complete the circuit. So if you complete the circuit now, you see that that same current that comes out of the battery or the energy source is the same current that flows through without branching. The current did not branch. So the same current flow through resistors in series. But what about parallel? In parallel, different currents flow through resistors in parallel. So let's say this is the terminal. Let me complete the terminal. Let me complete the circuit. Remember, this is a symbol for battery. So the current flowing from this battery now, as you can see, it is not the same current that flows through these resistors. Instead, that current branches into each of these resistors first and then joins back again to get the main current of the cell before flowing back to the battery. That is the current principle in understanding the difference between series and parallel arrangement. Now, what about the voltage principle? Now, for voltage principle, it is the opposite. Resistors in parallel have the same potential difference across their ends. Resistors in parallel have the same potential difference across their ends. So let's say this cell is rated 12 volts. Each of these resistors in parallel, they are going to be rated, the PD across their ends is going to be 12 volts. This one is going to be rated 12 volts. This one is going to be rated 12 volts. This one is going to be rated 12 volts as well. But the voltage across resistors in series is different. It is not the same. Because the PD across this end and this end is different from the PD across this end and this end, which is also different from the PD across this end and this end. So each of these resistors you are seeing here, they are going to have their own voltage. That is the voltage principle. Watch this explanation as many times as possible until you get it, because this is the foundation which we are going to be working with to solve numerous questions. Okay, so let's take a case, for example. Let's say we have a setup like this. Let's say we have a setup like this, and then this setup branches here. This is a combination of both series and parallel. right? Yes, this is a combination of both series and parallel. So let's say this is the terminal. You connect it to a cell. This is the terminal. How do you resolve these resistors? Let me assume, see, throughout the examples I'm going to be drawing, let's assume each of the resistors are just 1 ohms each. So each of them, they are just 1 ohms, so that we can simplify easily. Okay, how do we get the net resistance? How do we calculate the net resistance in this circuit? Well, first of all, I want you to remove the resistance in parallel first. Always do parallel so that you can now handle series. As you can see, this resistor is in series with this resistor, which is in series with this parallel combination. So if we can resolve this parallel, we can easily add up all the resistors in series. So the combination of these two resistance in parallel is given by the formula what? Remember, 1 over R is equals to 1 over R1 plus 1 over R2 to as many resistors, right? So the total is going to be given by 1 over R is equals to 1 over R1 plus 1 over R2. So that's going to be what? 1 over 1, that is the first resistor, plus 1 over 1. Maybe I should have used different digits. Let me try using 2. Okay, so let's use 2 instead. Let's say this is 2 and this is 3 for the sake of understanding, so you don't get confused. Okay, so 1 over R1, let's say this is our R1, 1 over 2 plus, let's say this is our R2, 1 over 3 ohms is equals to 1 over R. It is not equals to R. Please take notes. Students always make that mistake. So how do you simplify this? Take the LCM. 2 times 3 is 6, right? 6 divided 2 is what? 3. 6 divided 2, 3. 3 times 1, 3. 6 divided 3 is 2. 2 times 1, 2. So 3 plus 2 is equals to 5 over 6. Therefore, R is equals to what? You invert. R is equals to 6 over 5 ohms. That is the total capacitance. So the circuit diagram will now be something like this. It will now become something like this, where the net resistance here is now what? 6 over 5 ohms, and we still have our normal 1 ohm resistors. So the net resistance now will be, or the total resistance is going to be what? 1 plus 1 plus 6 over 5 ohms. Because what? Because R total in series is equals to R1 plus R2 plus R3. Let's take another case. Another case where we have a resistor and that resistance, then you have one resistor here, you have another resistor, you have another resistor, and then probably I can add another resistance here, right? How do you simplify this circuit if the cell connected is like this. Now remember, when two terminals are joined, they are in what? They are in parallel. Don't just rush and go and say, okay, we can just simplify these two because they are joined end to end. They are joined end to end now, but we cannot say this is in series because there's also another division here. So you cannot rush like that. That's why I said you should always what? Simplify parallel before series. So two resistors in parallel here, which are this one and this one. So let's call it arrow 1 and arrow 2. How do we resolve this? Your normal formula for parallel. And then when you're done, you have a net diagram that looks like this, where these two resistors are now combined to form one. So it will form one resistance, and then you'll be left with a circuit that looks like this. So to completely solve this, all these resistors here, they are in series. Why are they in series? It's because the same current flows through them. Let's check the flow of current. The same current flows through them without any branching. That's why they are in series. So now that you have understood the concept, let's answer this question. So in this question, the total resistance measured at PQ in the diagram above is. So like I said, okay, this one is even a different case. So how are we going to tackle this case now? Pause and try to attempt this question yourself. Okay, so let's solve. First of all, I'm going to find how. I know I said you should always do parallel first, but I can't really see a parallel resistor here. These two are not in parallel because they are not directly connected end to end. There's a resistor between them. But this and this, they are in series. This and this, they are in series. There is a continuous flow here without branching between these three resistors. So they are connected end to end, which means they are in series. That means I can first resolve those ones to get a total. So arrow is equals to what? 2 plus 2 plus 2. That is resistors in series, right? 6 ohms. And then my diagram will be something like this. All these resistors will combine to form a 6 ohm resistor, and then what is left is going to be 3 ohm resistor in parallel, because remember, these three resistors are gone. They have combined to form this 6 ohm resistor. So I have 3 ohm, which is this 3 ohm here, and then we complete the diagram. Let's simplify further. So we have 1 ohm, you have 1 ohm here. So let's continue simplifying. Now these two are in parallel. So how can we resolve parallel? Remember, parallel resolution is 1 over r equals 1 over arrow plus 1 over arrow. Now there's a shortcut. There's a shortcut you can do. The shortcut is arrow is going to be equals to what? The product of the resistance all over the sum of the resistance. This only works with two resistors. Product over sum. So we can find the net resistance of 6 ohm and 3 ohm, which are in parallel, as 6 times 3 all over 6 plus 3. 6 times 3 is 18, 6 plus 3 is 9, so 2 ohms. That means these two in parallel combine to give a net resistance of 2 ohms. If you still use this normal formula, try it out. 3 here, 6 here. Resolve until you get the final value for arrow. You get 2 ohms. This is just a shortcut formula for when you have two resistors in parallel. So 2 ohms combined, and then this is what we're left with, 1 ohm, and then 1 ohm, and then the terminals. These remaining resistors are in series because they are end to end. There's a continuous flow of current end to end. That means you can just add them up. So we can just say resistors, new resistors in series, right, is equals to 1 plus this 1 plus 2 plus 1. It's going to be equals to what? 4 ohms. Correct answer is C. Now, you may wonder, why was I able to do continuous current here and say, okay, these ones are in series? Somebody might ask that, or I had a student who asked that, why can I not do the same thing here and say these ones are in series? The reason is because there is a branch. It is not a continuum. There is a branch. Did you see any branching here? No. So please rewatch this as many times as you can until you get the concept. Let's solve this question. Sum of the current I1 and I2 in the figure above. So I1 and I2 in this figure, what is the sum of these two currents? First of all, the approach I would take to solving this question is to get the total capacitance in the circuit. So first approach is to get what? Total capacitance. Total resistance. Sorry about that. It's when we're treating resistors that when we make mention of capacitance. The total resistance in the circuit. So how can I find the total resistance in the circuit? So I have to resolve series and we have to resolve parallel. Well, straight away I can already see that these two are in series because they are just connected from end to end, right? We can just add them up. So 5 plus 10, we can just combine them, 15 ohms first. We're left with this. With a 12 volt okay, so this is a little bit difficult. It's a little bit difficult, but there is an easy way to go about it. Well, we are very sure, first of all, we're very sure that these two are in series. As you can see, there is going to be a continuous flow of I1. This is I1. There's going to be a continuous flow of current 1 across these two resistors around the circuit. So this is why these two are in series. We are right when we did that. So this one left, how do we resolve it with this? Are they going to be in parallel or are they going to be in series? One way to visualize this is I can redraw the diagram. See, in physics you have to be creative. I can redraw the diagram as 15 ohms and then I'm going to have the 12 volts here. Then this other 10 ohms is over the 12 volts. Right? So this is the same thing as saying, since these two are connected at both terminals, 10 ohms and 15 ohms are in parallel. That's what that means. As simple as that. Therefore, 1 over R is equals to 1 over R is equals to, or let's use our shortcut because it's involving two resistors, right? So let's use our shortcut. Our shortcut is R1 times R, sorry, R1, R2. I was correct, Shabo, for aesthetics. So R1 and R2 is what? 15 times 10 all over 15 plus 10. 15 times 10 is 150. 15 plus 10 is 25. 25 divided 150. So 25 divided 150 is 25 to 50 is 2. 2 times 3 is 6. So the answer is going to be 6. 6 ohms. Now remember, we have only gotten the total resistance in the circuit. Now that I've gotten the total resistance that is offered by all these resistors put together, we can then answer the question of what is the value for I2 and value for I1. Now, from V is equals to IR, Ohm's law, if you remember clearly, we can get the total current which is flowing in the circuit. We can get the total amount of current flowing in the circuit. Our voltage is 12 volts, which is supplying the entire circuit. Our current, that is the total amount, I total times R, which is what? The total resistance times R total, 6 ohms. Make I total subject of formula is equals to 12 over 6. So I total is going to be what? 2 ampere. That is the total current flowing in the circuit. Now that we know the total current flowing in the circuit, the total current is equal to what? I1 plus I2. The sum of the current branches to each resistor. Now, remember the rule of current. The same current flows through resistors in series, but different currents flow through resistors in parallel. Therefore, the case we are dealing with now is that we have a different current flowing to the 10 ohm resistor, which is called what? I2, and we have a different current flowing towards the 15 ohm resistor, which is I1. So to go about this, we can still use Ohm's law again. So Ohm's law is given as V equals IR. So what is the voltage across this resistor? It is also 12 volts. What is the current? We don't know what the current is, but we know that the resistance is 15 ohm, right? And we know that the resistance here is 10 ohms. So 12, sum of the currents I1 and I2. Oh, we already solved the question now. So I found the total current, which is 2 ampere. Therefore, the correct answer is D. But if you want to find the individual values of I1 and I2, we can keep on solving. So in place of voltage, where I go to write 12 is equals to, so I'm solving for this first. 12 is equals to I2 times what? Times the 10 ohm resistor. So I2 is equals to what? 1.2 ampere. Now let's solve for the other one, this other resistor. So 12, remember 12 volts is constant, voltage is constant in parallel resistors, is equals to I1, that is this I1, times what? The resistance here, times 15. So we have what? I1 is equals to, dividing this, it will give you 0.8 ampere. So as you can see, if you add 1.2 to 0.8, you are going to get the total current flowing in the circuit, which is 2 ampere that we calculated for initially. Is this still making sense? Can you see how everything interacts, everything adds up? So you can see a Jamb question like, what is the current flowing through the 10 ohm resistor? Don't crack your head too much. The current flowing through the combined resistance is the same current that is going to flow through this 10 ohm resistor. So I1 is the current that flows through what? The 5 ohm resistor and the what? And the 10 ohm resistor. So if you ask the question like that, the answer is 0.8 ampere. The 0.8 ampere that passed here is the same 0.8 ampere that we pass here because they are in series. Okay, so this is another case. You can pause the video and try to attempt this one yourself. All right, so let's solve the question. An electrical circuit is connected up as shown above. What is the value of the current passing through the 1 ohm resistor? So I'm looking for the current passing through the 1 ohm resistor. First off, what I can see is that these resistors here, if I can resolve them into one resistor, this 1 ohm resistor is going to be in series with the combined resistance here, and there's going to be a continuous flow of current around. Therefore, the total current passing through the circuit rather, is going to be the same current that will pass through this 1 ohm resistor. In that vein, we know what to do. We have to find what? Use the Ohm's law. Ohm's law states what? Ohm's law states that V is equals to IR. That means the voltage in the cell in circuit is equals to the current, the total current, times what? The total resistors or the total resistance in the circuit. So how can we calculate the total resistance in the circuit? How do we do that? Well, first of all, we have to simplify this. This is where the problem is. This is where the problem is. How do you know which one is in parallel? How do you know which one is in series? Follow the movement of current. So let me use a red marker now to continue the movement of current. When the current comes here, it branches into this 3 ohm resistor and it branches into this 3 ohm resistor. Anywhere you see a branch like this, just know that those two resistors are in parallel. So this 3 ohm and this 3 ohm, they are in parallel. But there is a continuum here. That means this 3 ohm and this 3 ohm, they are connected end to end. That means they are in series. And then these 3 ohm and these 3 ohm are connected end to end. That means they are in series. So let's resolve the series first because that's the easiest in this case. So we're going to have what? 3 plus 3, which is a combined 6 ohms. 3 plus 3, which is a combined 6 ohms. And now we have two 6 ohm resistors which are in. We have two 6 ohm resistors which are going to be in parallel. So now we have to resolve these two 6 ohm resistors which are in parallel by using the normal formula we know, right? So let's use our shortcut formula. R is equals to, that ink is too dull. Let's use purple. R is equals to what? R1 times R2 all over R1 plus R2 This is a shortcut formula. The original formula is what? 1 over R is equals to 1 over R1 plus 1 over R2 and so on for as many resistors in parallel. So 6 times 6 all over 6 plus 6. So 6 times 6 is 36 over 12. 36 over 12 is what? 3. So the combined resistance here, is equals to what? 3 ohms. So we have a combined resistance of 3 ohms. Here's what the new circuit will look like. 3 ohms and then this 1 ohm resistor. So how do we resolve this? They are in series obviously, so we just add. So 3 plus 1 is what? 4 ohm. So the combined resistance, R total in the circuit is what? 4 ohms. And the voltage is what? The voltage is 12 volts if you look at the circuit. So voltage 12 volts, or no need to put in it, is equals to the total current times what? The total resistance, which is calculated as 3 ohms. So I total is equals to hold on, hope we didn't make a mistake. 12 volts, we got what? 6 times 6, 36 over 12. We got 3 ohms here, total 3 ohms plus 1 ohm, 4 ohms. So it is 4 ohms we got as the total. Sorry about that. You can backward the video and see that it's actually 4 ohms we got. So I total is going to be equal to what? 12 divided both sides by 4. We're going to have 3 ampere. So 3 ampere is the correct answer. This was a very tough case. This is a 1990 something Jamb question. So capacitors just take the opposite of resistors for parallel and series resolution. The current and voltage principles remain the same. Instead, we have it's not current and voltage principle. Instead, in place of current, we have charge. Because the formula for capacitance is Q is equals CV. So for capacitors, if we have the symbol for capacitor is this is the symbol. So if you have two capacitors in series, don't rush to go and add them, because we said resistance in series is equals to R1 plus R2. For capacitors in series is given by 1 over C for 1 over C1 plus 1 over C2. So it is the opposite. In order not to confuse you, just learn the one for resistors, and anytime you are dealing with a capacitor, use the opposite. So now these two are in series. Let's say this is 1 microfarad and this is 3 microfarad. The total capacitance here, since they are in series, is going to be what? It's going to be, we can use our shortcut here to C1 times C2 over C1 plus C2. So that is 1 times 3 over 1 plus 3. That is 3 over 4 microfarads. That's the answer. It is the same thing as using this formula here. Let's try it out. 1 over C is equals to 1 over C1. Our C1 is 1 over 1 plus our C2 is what? 3. So 1 over 3. Take LCM. LCM 1 times 3 is 3. 3 divide 1 is 3. 3 times 1, 3, plus 3 divide 3 is 1. 1 times 1. And we are left with what? 1 over c here. So we have equals to 4 over 3. So you have 4 over 3. To remove this 1 from the top, you have to invert. So inverting, you have to invert these 2. You have 3 over 4, which is the same answer we got. Just trying to show you. Then for parallel connection in capacitors, where you have something like this, for parallel connection is much more easier in capacitors, because now you just add the total capacitance is going to be equal to C1 plus C2. Not to waste time. Now the charge and voltage principle. Voltage principle in capacitors remain the same. It remains the same. While the charge principle is similar to the current principle in resistors. Remember that in resistors we said the same current flows through resistors in series. In capacitors, it is the same charge that flows between two capacitors in series, but different charge exists between capacitors in parallel. Now when it comes to voltage, different voltage between capacitors in different potential difference between capacitors in series, and different and the same potential between capacitors in parallel. So the concept is, you get it. When we take a question, you will understand deeper. Okay, so using the circuit diagram above, calculate. What am I even doing? This question is, I made up this question, but I made a mistake. The question is supposed to be calculate. Wait. V equals. The question is supposed to be calculate the charge in the circuit. It's supposed to be calculate the charge in the circuit. Anyway, this question is wrong. It is very, very wrong. So you know what we're going to do? Let's just find the net capacitance and the charge in the circuit. That's what we're going to do. So the net capacitance, or the total capacitance, is given by what? We have to resolve the series and the parallel. So capacitors in parallel, these two are in parallel. Remember, in parallel for capacitors we add, but for resistors we do that 1 over. So 40 plus 60 is this total combined is 100 microfarad. To be fast, I'm just going to be doing it. So we have 100 microfarad in series now. You don't add them because this is capacitor, not resistor. So we have to use our parallel formula for capacitor. I mean our series formula for capacitor. This is series formula in capacitor. So 100 times 100 all over 100 plus 100. This is going to give us what? 100 times 100 all over 200. Zeros cancel out. So I'm going to be left with 100 over 2. That is going to give us 50 microfarad. So the net capacitance, or the total capacitance, is equals to what? 50 microfarads. Now what about the charge in the circuit? The charge in the circuit is given by the formula Q is equals to CV, like I explained before. So what is the charge? C. This is the capacitance, remember. So capacitance is what? 50 microfarad times what? Voltage 24. So I have to multiply 50 by 24. Remember 24 volts, this is where I got it from. So we have 1200. So it's equal to 1200 microcoulombs, because we use microfarad to solve. If we want to convert this to coulombs, we use 10 raised to power times 10 raised to power minus 6. And so final answer is going to be, take this 1 2 3 1 2 3. So 1.2 times, you have to remove 3 from 6 there. We're going to be left with 1.2 times 10 raised to power 3 coulombs. And that is the correct answer. Okay, question 15 is a different question. Okay, so two resistors, 5 ohm and 10 ohm, are arranged first in series and later in parallel to a 24 volt source. Read the question very well. First in series. So in series, we already know that the combined resistance in series is going to be 15 ohms. Just add them. This is resistor, right? So for series. Then for parallel, it's going to be what? 5 times 10 all over 5 plus 10. That is 50 all over 15. 50 divided by 15 is what? I could just leave it as a fraction. 5 here is 3, 5 here is 10. So we have 10 over 3. This should give me 3.33. Well, I'm going to leave it as a fraction. 10 over 3 ohms. Okay, so to a 24 volt source, the ratio of the total power dissipated in the series and parallel arrangement respectively is, okay, so formula for power is equals to IV. So since power is equals to IV and they're asking us for the ratio of the total dissipated power in series and parallel, we have to what? Take the ratio of series IV to parallel IV. What does that mean? So if we say IV ratio IV, remember something, that the voltage is the same, right? But the resistance were different. And since power is equals to IV and V is equals to I arrow, therefore power is equals to I squared arrow. So we have to take ratio of I squared arrow to I squared arrow. For series, what we had for our resistance was 15. For our resistance in series. For parallel, what we had for our resistance is 10 over 3. So I'm going to write 10 over 3 there. Now the current is also probably going to be different, because remember V is equals to IR, right? So from here we can find current. Therefore, current is equals to V over R. That means the voltage source 24 all over resistance 15, right? I can just write that there, 24 over 15. So since V is equal on both sides, the voltage in the circuit is the same, we can just write V in place of 24. I'm teaching you a hack. So in place of 24, we can just write V, because I know it's going to cancel out I can see in the future that is going to cancel out later. So for current in series, V over 15 squared ratio. For parallel, it is V over 10 divide 3. So that is what? V times 3 over 10. Right? So that's 3V over 10. So we have what? 3V over 10 squared. Now we have to simplify further. This Jamb question is a little bit hard, sure. I will not lie. Takes that hard small. V squared, square into the brackets, all over what? 15 square. I'm just going to leave 15 like that. 15 square times 15 ratio 3V square. 3V squared is going to be what? 6V square. Don't forget to square the 3 as 9V square. Don't forget to square. Wait, so square in brackets. Okay, 9V square. Don't forget to square the 3 as well. All over 10 squared times 10 over 3. Remember, we took a convention, right? We took this side as series and this side as parallel, so you don't get confused. And they say we should take what? Ratio of total power dissipated in the series and parallel arrangement respectively. So the ratio of series to parallel is what we are trying to do. Now V square, will cancel out V square from the other side clearly. 15 here, 15 here, we have 1 and we have what? 15 left here. So 10 here, we have 1, and then 9 here. Okay, 3 here, we have 3 into 9, and then 3 here, we have 1, and so almost everything is cancelled out. And we are left with what are we left with here? We are left with 1 over 15. Let me use a different color so you can see clearly. So we are left with 1 over 15 is equals to, this 1 over 15 is equals to 3 over 10 times 1 over 1. 1 over 1 is 1 times 1 is the same as 3 over 10. So ratio 3 over 10. So cross multiply, we're going to have 10 is equals to 3 times 15. 3 times 15 is 45. So we have Jamb not try, sha. Jamb not try for this question. So we have 10 ratio 45. 5 here to 5 here. 5 here is going to give us 9. So the answer is 2 ratio 9, which means I can't see 2 ratio 9 in the option. Therefore, the correct answer is no correct option. You see why I say Jamb not try for this question? So after all that stress, we ended up with no correct option. Please, if you don't understand it, watch this part again. I explained it very well. This may not be the best approach to solving it, but yeah, it is what it is. An easier way might have been to leave out the value and just use the terms and cancel out. But I was just being creative. So say power dissipated. We already established the fact that power is I square R, Abi. And we already established the fact that from V is equals to I arrow, I is equals to V over R. So I think that was how we substituted into I here. We now squared it times R. So we're actually making things unnecessarily long. This is already an established formula. I'm going to end up at, so another formula for power is actually V square over R. We should have just used this straight instead of beating around the bush. We should just use V square over R ratio V square over R, taking this side for series and this side for parallel. And then our voltage source, because it's the same, we can just strike out. Our voltage source is the same, Abi. We're left with resistance in series and resistance in parallel. Our resistance in series is 5 plus 10, that will get 15, so it's 1 over 15 ratio. We have 1 left here, all over. Our resistance in parallel is what? Our resistance in parallel is 5. Okay, that is if you were to arrange this in parallel again with this same voltage. It is going to be what? 5 times 10, 50 all over what? 15, and simplified to 10 over 3. So it's going to be 1 over 10 over 3, something like this. Or a better way to put it is 1 over 15 ratio 1 divide, so that is going to be like times 3 over 10. Let's bring that 3 here. 1 times 3 over 10. And so yeah, everything is simplified already. If you cross multiply, you're going to get 10 ratio 45, and then we still going to arrive at our initial 2 ratio 9. So the answer is not there, but this is the shortest method we could have used to solve the question. I was just being creative, trying to figure it out, and that's the same approach you should take. So for cell or battery, cell is a single unit of a battery. Battery is a group of cells attached to one another. That's why when you look at for this symbol of cell, you just see a single unit. But for battery, you see multiple units of cells joined together. So this is an example of a battery with 2 cell units, while this is a cell. That's the difference. Conventional flow and electron flow. Okay, let's recap. I already treated it. The longer line represents positive, the shorter one represents negative. Conventional current flow is from positive to negative. Then electron flow convection is from what? Is from negative to positive. Let me put it like this. It is from negative to positive. That is the opposite direction. Alright, now that I've done conventional flow and electron flow, parallel and series resolution, currents and voltage principles for cell or battery. We already know what the symbol of cell is. This is the symbol of cell and battery. So for cells, it is very easy. When you have cells in series, you just treat them like you would treat capacitors. So you have one cell joined to another cell, joined to another cell. Let's say each of this is 4 volts, 3 volts, and 1 volt. The total EMF or the potential or the voltage is equals to V1 plus V2 plus V3, or another way you can say is E1 plus E2 plus E3. E represents EMF, V represents voltage. Anyone works. So you add them together, 4 plus 3 plus 2, the total voltage offered by these cells. Then there is a little bit of a difference when it comes to cells in parallel. So for cells connected in parallel, it is just the single cell. So we have cell 1, cell 2, cell 3. The net EMF of these cells in parallel is equals to one of the cells. That means cells connected in parallel have to be equal. That means you can only connect similar cells in parallel. You can only connect 2 volts, and another 2 volts in parallel. You cannot go and connect 2 volts, 3 volts, and maybe 4 volts in parallel. It's not possible, like you have in unlike you have in resistor or capacitors. So each of these cells have internal resistance. Now the internal resistance of the cell is going to be gotten by just the way we resolve resistors. So for cells in series, the internal resistance, the total internal resistance offered by each of the cell can also be gotten by what? Adding up the resistance, internal resistances. For cells in parallel, the internal resistance of each of the cell can also be gotten by using what? The formula for resistance in parallel. So 1 over R total equals to 1 over R1 plus 1 over R2 plus 1 over R3 and so on and so forth. Now, something to note is you have to know the direction of connection of each cell, because in series there's something special. There's a special case. If you have a battery connected, it has this negative. Remember, the short term is negative, long term is positive. It has to be connected to the positive terminal of the other battery. This is the right connection. But we can have a wrong connection where you have the cell, the negative part is connected to the negative of another battery. So in this case, this is a wrong connection. In this case, the cell that is in the wrong direction will attract a negative sign. So let's say we have what? Let's say, for example, this is 4 volt cell and this is a 3 volt cell. The net EMF here is given by what? 4 plus 3, because this is the right connection, right? But the net EMF here is going to be given by what? 4 minus 3. Minus 3, so that is 1 volt. Why the net EMF here is 7 volts. That's why you should always connect your cells in the right direction, the correct direction, from negative to positive. But this one is from negative to negative, which is wrong. So I'm trying to be fast here because we still have a lot to cover. Okay, so take a look at this case. 3 EMFs, 3 cells of EMF 1.5 volts and internal resistance 2.5 ohm are connected in parallel. Find the net EMF. Once you see parallel for EMF for cells, the answer is 1.5 volts. So I answer between option A and option B. What is the net internal resistance? Okay, the internal resistance, since it's in parallel, we have to do the resistance in parallel. That means what? 1 over 2.5 plus 1 over 2.5 plus 1 over 2.5 is equals to 1 over R total. So we have to get LCM. LCM is 2.5 because they are the same, right? 2.5 divided 2.5 is 1. Everything is going to be plus 1 plus 1. So everything is going to be 3. 3 over 2.5 is equals to 1 over R. Therefore, R total is going to be equals to, just invert 2.5 over 3. So 2.5 divided 3 is going to be 0.83 ohms. And so B is our answer. Next question. Next question says, next concept, internal resistance of a cell. So we're going to talk about terminal voltage, loss voltage, external resistance, internal resistance. Take a look at this diagram, for example. So this is the cell, this is the battery, this is the internal resistance, this is the load or the external resistance, and this is the battery. The battery has an internal resistance. That is why a battery rated 5 volts might not necessarily have a potential difference of 5 volts. It will have a potential difference of less than 5 volts. It will have a potential difference of less than 5 volts because of internal resistance of that cell. It is stealing some voltage, and that voltage is called lost voltage or lost potential difference. So this is the formula, equals I arrow plus I arrow. So the formula is I in bracket arrow plus arrow. How did we even come about this formula? It's by adding what? The total voltage these are in series. The internal resistance and the external resistance are in series, and I told you that they have what? They are going to have different voltage, right? So we can call this one V1. We can call the voltage here V2, right? So the total EMF of the cell, the total voltage, is going to be equal to V1 plus V2, and V1 is going to be equal to the, since they are in series, as you can see, they are in series, then the same current is going to flow through them. So we can just call the current I. So we know that V is equals to I arrow from Ohm's law, right? V equals to I arrow. Therefore, V1, we're going to simplify it, the resistance times the current. So we already know that the current is the same. So I times what? Internal resistance, right? Or let's start with the external resistance. External resistance for, okay, V1 is to internal resistance, so let's do that. I arrow plus what? V2 is what? The same I times external resistance arrow. And that's how we arrived at this formula. So this voltage here, because V is equals I arrow, is the loss voltage from the original EMF of the cell. The PD, the external, that is the terminal PD, the terminal voltage, that's the voltage across the terminal of the load, is given as what? The current in the cell times the resistance of the load. It is always, terminal PD is always lower than the EMF of the cell. When we solve a question, you understand. So a cell whose internal resistance is 0.5 ohm, I'm just going to write my parameters and I'm going to be quick about it. So internal resistance R is equals to 0.5 ohms and what? Delivers a current of 4 ampere. So current is equals to 4 ampere to an external resistor. We don't know what the external resistor is. The loss voltage of the cell is what? Okay, so they're asking us of loss voltage. What is the formula for loss voltage? IR. This is the internal resistance times current. That's the loss voltage. So we just have to multiply 4 ampere and 0.5. That is so easy. So our answer is B. A resistor of resistance R is connected across the cell if terminal PD of the cell is reduced to 1/4 of its EMF. So this is the formula. Terminal PD is reduced. Remember, terminal PD is IR, right? I capital letter R. Terminal PD is reduced to 1/4. If I'm to interpret this question, so I'm going to write it like this. Terminal PD is equals to 1/4, that is 1/4, the EMF of the cell. 1/4 times the EMF of the cell. Express the internal resistance R of the cell in terms of R. So how do we go about this? What is EMF of the cell? EMF of the cell is I bracket R plus R, right? Over 4 is equals to IR. Current is going to cancel out, so I'm going to have 4R is equals to R plus R. So we're asked to express the internal resistance in terms of what the external resistance R. Therefore, the internal resistance is equals to what? 4R minus R, which is equals to 3R. And this is the correct answer. Efficiency of a cell. Efficiency of a cell is the percentage output of a cell. Remember, we said that the EMF of the cell is higher than the terminal potential difference is always lower than the EMF of the cell, because there is some voltage lost because of this internal resistance. So the power output is always lower. So the efficiency of a cell is not 100%, it is less than 100%. A 100% efficiency cell will deliver its terminal PD the same as its EMF. So the EMF is going to equal to terminal PD if a cell is 100% efficient. Now, since cell is not 100% efficient, it just means that what? We have to take the ratio of the power output, that is the output voltage, which is that of the external load. So V equals to IR, V equals to IR. Output voltage is going to be what? IR, because external resistance, right? Over input voltage. What's the input voltage? Remember, the EMF is equal to the voltage lost here and the voltage lost, that is V1, plus voltage lost here, V2. Plus the voltage supplied to the load. So it's going to be what? I bracket R plus R. Current cancels out and we're left with this. That's the ratio times 100 is expressed in what? Percentage. That's why we have this formula for efficiency. So calculate the efficiency. Okay, they give us efficiency here. Calculate the value of R. So 75% is saying 75 over 100 equals to, or rather, another way to put it is, whenever you're using over 100 here, you don't need to do times 100 again. So anyway, let me just write the efficiency. Efficiency is equals to what? Efficiency equals to R over R plus R, right? Times 100. So 75 is equals to, what's the external resistance? 6 ohm resistor over 6 plus R times 100. We can just say 600 cross multiply, so we have 75 bracket 6 plus R is equals to 600. 5 here is 5 times 12 is 60. 5 times 13 is 65. 5 times 14 is 70. So 5 times 15 has to be 75. And then 5 into 600, 12, so 120. Okay, so 5 can still go again. 3. 5 can go here. We're going to have 5 times 20. So 25. Is it 25? No, 24. So 3 can go again. Hey God. 3 can enter 24. That's going to give us 8. So we're left with 6 plus R is equals to 8. Therefore, R is equals to 8 minus 6. That's going to give us 2 ohms. So these are correct answer. Electrical energy and power. So these are different formulas for electrical energy. Therefore, power is going to be equals to what? Remember, work done is equals to power times time. Work done is the same thing as energy. So we can say H is equals to power. What am I even saying? Yes, work done is equals to power times time. So H is equals to power times time as well. Electrical energy is lost in form of heat. So if they are asking you to calculate the heat dissipated due to electrical energy, is I square RT or IVT or V squared T all over R. The heating effect of current is what, anyway. So making power, so the formula here is equals to work done over time. Power is work done per unit time, or the time rate of doing work. Abi? So each of these formula here, you divide time, you're going to get power. I square RT divided by time, T leaves. Just remove all the T's and you have formulas for power. So power can be I square R, power can be H equals IV, power can be equals V square over R. Commercial electricity is sold in units of kilowatt hour. So it's given by the formula cost equals to power times time times the amount. Remember this formula, please. 100 kobo is equals to 1 naira. So please learn how to convert. If you are given naira in your question and you are given naira in your unit, in your options, no problem. But if you are given kobo in your question, for example 600 kobo in your question, and in your options you are saying naira, please convert from kobo to naira first. So how do you convert? If 100 kobo is equal to 1 naira, then 600 kobo will be equals to x is equal to 6 naira if you cross multiply, right? So that's how to convert. Then kilowatt hour. Note, electricity, the unit it is measured in, it is in units of kilowatt hour. So on no account should you leave your final answer in watts. Even if they give you watts in your question, convert watts to kilowatts. How do you convert from watts to kilowatts? You divide by 1000 and you get kilowatts. Okay, so take this question. Heater takes, what are they calculating? The cost of electricity. Remember, cost is equals to power times time times what? Times amount per unit. So what is the power supply? The power is equals to, we have voltage, we have current. One of the formulas for power is IV. So V, that is 250 times 4. That is 4 times 250 that is 1000 watts. That is equivalent to kilowatts. 1 kilowatt after dividing by 1000. Then what? Time, 5 hours. Okay, you need to learn how to convert from, okay, it's in hours, so kilowatt hour. No need to convert time to seconds because it is measured in kilowatt hours. So we can just multiply by 5. So 1 kilowatt hour times 5 times what? The amount. What is the cost of electricity? What is the cost of the electricity consumed at 10k per hour? 10k here is not 10,000 naira. It is not 10,000 naira. This is 10 kobo. Remember, so because 100 kobo is equals to, some persons will go and think it's 10,000. because 100 kobo is equals to 1 naira. Therefore, 10 kobo will be equals to what? X. Cross multiply, you are going to get 10 over 100. That's going to be 0.1 naira. So the rate is 0.1 naira per kilowatt hour. Times 0.1. Okay, we also have options. We have some options in kobo and we have some options in naira. So how do we know which one is correct? Anyway, let's find out. So times rate. I'm supposed to write so correct this formula, please. Amount is a little bit confusing. Just write rate. That is the amount per kilowatt hour. So the amount per kilowatt hour we just calculated as 0.1. It is 0.1 naira per kilowatt hour. So 0.1 times this power times time is going to be equal to what? 0.1 times 5 is 0.2. Did I get that correctly? 5 times 0.1. 0.5, sorry. Oh, I'm so exhausted. 0.5, and this is cost in naira. There is no 0.5 naira in option. So I have to convert 0.5 naira to kobo. How do we convert? If 100 kobo is equals to 1 naira, then how many kobo is going to be equals to 0.5? It's 50 kobo when you cross multiply. So the correct answer is B. A man has 5 60-watt bulb and a 240-watt heater in his apartment. If the bulbs and water heater are switched on for 4 hours daily and the cost of electricity is 1.2, so this is the rate. Actually, whenever you see per kilowatt hour, that's the rate. So cost is equals to power times time times the rate, right? The power consumed is 5 60-watt bulbs plus a 240-watt heater. Total is what? 5 times 6 is 30 plus this. Okay, so 540 kilowatts. Sorry, 540 watts, because these are in watts, right? So I'm just going to leave it there first. Then they said use it for 4 hours daily. So for every day for 30 days at 4 hours. Okay, so power times time, the total time or the total hours is 4 hours times 30 days. So the total hours is 4 times 30 days. That's 4 times 3 times 12, 120 hours. That was the total hours you used it. So the total power times the total hours. But we have to convert this to kilowatt too. So you divide by 1000 is equal to 0.54. So 0.54, that is the power in kilowatts, times the hours, 120, times the rate. The rate is 1.2 naira. So 1.2. The bill or the cost is going to be equals to what? 0.4 times 120 times 1.2 because wait, did I make a mistake? Calculate his bill for 30 days. 1.2 per kilowatt hour. Heater are switched on. 5 bulbs. 5 times 3, 300. 300 plus 200, 540. That's correct now. 4 hours daily, and the cost of electricity is 1.2 per kilowatt hour. Ah, God, I went to write 0.4 instead of 0.54. So 0.54 times 120 times 1.2 is 77.76. This is the answer. Next question. So this is a recap. You have to do these questions yourself. Pause the video and try to attempt them. Pause the video, try to attempt these questions. Conversion of galvanometers. So to convert the galvanometer to an ammeter, you connect a shunt in parallel. And this is the formula. Current across the shunt times the external resistance is equals to current in the galvanometer times the internal resistance of the galvanometer. The total current in the circuit is given by the shunt current plus the current in the galvanometer. This is simple Ohm's law. Or current law. Rather, current principle that we treated before. So to voltmeter, you have to connect a multiplier in series to convert a galvanometer to a voltmeter. The reason why we connect a shunt in parallel to a galvanometer to convert to an ammeter is because galvanometer can only read small currents, right? So to convert it to an ammeter is a device that can read larger amount of current. So for a galvanometer, which is a very sensitive device, I can only read small current, we have to divert a large amount of that current through a low resistance shunt, a low resistance wire or shunt in parallel with the galvanometer, so that we divert a large amount of current away. So this is the galvanometer. You have to connect a shunt in parallel with the galvanometer. So this is the current entering the circuit I. The galvanometer has its own current. It will branch there, but a larger amount of the current would go through the shunt, a resistor of low resistance, and divert it away from the galvanometer so that the galvanometer will not get bad. And this is what we came up with. For a voltmeter, we connect a multiplier in series. Just normal principles. When you connect multiplier in series, what happens? Voltage is what? The voltage is going to be different, but the current across is going to remain the same. So a multiplier will divert some voltage from the galvanometer. So if we connect the galvanometer with a multiplier in series, a multiplier is a high resistor, is a high resistance. That's not a symbol for resistor, but let's just manage it. So we are connecting it in series, therefore that high value resistor is going to divert a high amount of voltage from the total voltage. Because galvanometer is so sensitive, it will not be able to read a very high voltage. A voltmeter is a device that can read high voltage. So to convert galvanometer to voltmeter, we connect a multiplier, which is a high resistance, in series, which is going to what? Divert some of the voltage to itself. So V1, V2. Here, V2 corresponds to the voltmeter of the voltage of the across the multiplier, the PD across the multiplier, and V1 here represents the This is supposed to be V subscript G. VG here represents the voltage or the potential difference across the galvanometer. Is that understood? Why this V is the cell which is being measured, the high voltage cell or high voltage source which is being measured. So just remember this formula and this for ammeter, and remember this and this for voltmeter, and you are good to go. An ammeter with full scale deflection of 10 milliampere has an internal resistance 0.5 ohm. Calculate the resistance of the shunt required. So I shunt RO is equals to I galvanometer internal resistance of the galvanometer. So where we have internal resistance, we're going to put internal resistance there, 0.5. What's the current in the galvanometer? Adapt it to read up to 3 ampere, right? Full scale deflection of, so the ammeter, which is the galvanometer that will be converted to an ammeter, is reading 10 milliampere. So 10 milliampere, I galvanometer is 10 times what? 10 raised to the power minus 3 in ampere. So resistance, okay, they say we should calculate the resistance of the shunt. So we have to calculate resistance of the shunt times current which is diverted to the shunt is 3 ampere. Or is that so? No. To adapt it to read up to 3 ampere. Yes, I think that's it. No, that's not it. To read up to 3 ampere, that means the current that's going in, this current that is going in is what is reading, right? So to read up to 3 ampere, therefore 3 ampere, there is the current going in, is equals to the current through the shunt plus current through the galvanometer. Therefore, to calculate I shunt here, we're going to use this formula. So I is equals to Ig plus I through the shunt. Therefore, 3 ampere is equals to the galvanometer, that is 10 times 10 to the power minus 3 plus I shunt. Therefore, I shunt equals to what? 3 minus 10 times 10 raised to the power minus 3. We have to subtract it. I shunt is going to be equals to what? 10 times 10 raised to the power minus 3 is 10 raised to the power minus 2. That is 0.01. 0.01. Okay, 3 minus 0.01 is going to be what? So you don't make a mistake. That is 2.99 ampere for the shunt. So instead of, we don't write 3, it's 2.99. So times this, we're going to get 0.01 times 0.5 over what? 2.99. And so 0.01 times 0.5 got 0.05. No, 0.005. All over 2.99. You can easily press that your Jamb calculator. 0.005 divide 2.99. I'm going to have 1.6. So your Jamb calculator is going to give you 0.7, I mean 0.17, 0.0017. That is option A. A galvanometer of internal resistance 10 ohms has a full scale deflection with a current of 10 milliampere. So we already have calculate the magnitude of the resistance required to convert it to a voltmeter. So I convert it to a voltmeter. What formula did I ask you to remember? I asked you to remember this formula, IR over I, right? So we have current 10 milliampere we have internal resistance R as 10 ohms. Then we have what? Measuring up to 3 volts. So the voltage is measuring V is 3 volts. Therefore, calculate the magnitude of the resistance. So we are calculating the external resistance R. So substituting the formula, we have 3 minus IR. What is I? 10 milliampere. 10 milliampere is 10 times 10 raised to the power minus 3 ampere times what? R. R is 10 ohms over I. I is 10 times 10 raised to the power minus 3. So we just simplify. This is going to give you 2 point. I think we have been here before. 2.99 over this over 0.01. 2.99 divided 0.01. You have 299. Supposed to have 299. Or did I solve something wrong? No, I didn't. 3 volts, 3 minus ampere, okay, times RO, internal resistance, 10. The answer is 299. 299 ohms. I think this is the closest answer. That is the closest answer. So we stick with that. Okay, potentiometer. Potentiometer is a device that precisely measures potential differences. It is used to compare or measure the EMF of cells. It is used to compare or measure resistances. So I'm just going to be fast with this. Potentiometer, as you can see, this is a jockey. Jockey is used to slide along the length. AB is a metallic wire, right? It's really 100 cm long. So as we slide the jockey along the length, as the length increases, the voltage or the EMF reading increases as well. So we have voltage is directly proportional to length. That means EMF is directly proportional to length. Introduce a constant. We have E is equals to KL. Therefore, E1 over L1 is going to be equals to E2 over L2. This is the formula you just need to remember. Just remember those formulas. This formula, rather. So, anytime you are given a question on potentiometer, just take E1 over the corresponding length, then E2 over the corresponding length. So, potentiometer question. If the cell is replaced by one of EMF, calculate the new balance length. Okay, so the balance length is going to be given by what? E1 over L1 is equal to E2 over L2. What is our E1? Cell of EMF 1.6 volts, 63 over L1. L1 is 85 cm. The reason I did convert is because length cm will cancel cm on both sides. So E2 is what? 1.07. What's the new balance length? L2 is going to be what? Cross multiply and let L2 stand alone. So L2 is going to be equal to 85 times 1.07 over 1.63. 85 times 1.07, 90.95 divided by 1.63 equals 55.8. So this is the correct answer. Approximately 55.8. So a meter bridge, you can just read this up, pause and read this. But the formula you should take note of is R1 over the resistor corresponding to the length is equals to the other resistor corresponding to the length, R2 over L2. similar to the formula of potentiometer. Wheatstone bridge can be used to determine unknown resistance as well, just as meter bridge. Variable resistor rheostat is used to vary the resistance until the galvanometer shows null or zero deflection. So for a Wheatstone bridge, the galvanometer must show null deflection. It must show zero deflection. So one of these resistors is a rheostat. It's used to vary the resistance until the galvanometer shows zero deflection. And when it finally shows zero deflection, an unknown resistance, one of them, could be unknown. We use the formula R1 over R2 equals to R3 over R4. So assuming R4 is unknown, you can use this formula to solve it. The other three, they'll give you the other three resistances. Simple AC circuits. So we're done with electricity. This is AC circuits, the last phase of electricity. Let's hurry up with it. So simple AC circuits, an AC, that is alternating current, is characterized by a wave-like or sinusoidal current and voltage. As you can see, it's like a wave. It's like a wave. That means it varies as you go up. The current increases and then starts to decrease again, decreases, starts to increase again. So it is not steady, it is not stable. It's increasing, decreasing, increasing, decreasing. It's a wave-like motion. That is alternating current for you. But direct current, which is known as DC, it just moves in a straight line as opposed to AC. So the sinusoidal equation is given by this: V equals to V naught sine WT, V equals to I is equals to I naught sine WT for current, for voltage. W is equals to 2 pi F. This is angular formula for angular velocity. WT is equals to phase angle of the voltage or the current. Not so important. What's important is this: peak and root mean square values of alternating current and voltage. The peak value of an alternating current is the maximum value. The maximum value. Go back to this diagram. As you can see, the maximum, the highest possible value is the peak current for this wave you can see here, and the maximum possible voltage is the peak voltage. Now, on the other hand, okay, since alternating current and voltage quantities which vary either positively or negatively, the root mean square value is the most useful way to describe them, because the values of current is always changing. It's always changing. So we have to find a steady value which we can be using to solve. That's what we call root mean square value. It is the effective value of current and voltage. So mathematically, we have what? I, that is current, root mean square current, is equals to what? Peak current all over root 2. Or we say peak current equals to 0.707 times what? Or we say root mean square current equals to 0.707 times what? Peak current. How do you get this 0.707? The thing is, peak over root 2. The thing is, 1 over root 2 is, if you press 1 over root 2 on a scientific calculator, you're going to get 0.707. That's how we have this, right? So for ease of use, just use this. So we can convert from peak current to RMS current using this formula. Same thing too for voltage. Calculate the peak voltage that could be obtained from a 220 volts. Okay, RMS main supply. So this is the effective value for voltage. VRMS is equals to the peak voltage all over root 2, or the best formula to use for ease of calculation is actually 0.707 peak voltage. So the peak voltage is going to be given by what? VRMS all over 0.707. So what is, so 220 over 0.707 going to give us our answer. That is 311 points. The reactance is the resistance offered by either a resistor, inductor, or capacitor in an AC circuit. Reactance is measured in ohms. Types of reactance. We have inductive reactance, which is given by the formula. So this is inductive reactance. The symbol is to represent it is equals to what? 2 pi frequency times what? Inductance. L means inductance. And inductance, the unit of inductance is Henry. Capacitive reactance. What is capacitive reactance? It's given by the formula XC is equals to 1 over 2 pi frequency times what? Capacitance. C there means capacitance. The unit of capacitance is what? Farad. Resistance is also a form of reactance, which is ohms normally. A capacitor of capacitance 4 microfarad was used in a radio circuit connected to a 50 hertz. That is frequency. The unit of frequency is hertz. Calculate its reactance. So how are we going to calculate reactance? Reactance of what? Capacitance. So we are looking for what? Capacitive reactance. Therefore, XC is equals to 1 over 2 pi FC, if you remember this formula. So 1 all over 2 pi, they say we should take pi as what? 3.14. So in place, I just put bracket 14 times what? Frequency is 50 times the capacitance is 4 microfarad. You have to convert from micro, so you say times 10 raised to the power minus 6, and this should give you your answer. 2 times 3.14. You can, because of time, you can just complete the solving and choose the correct answer. An inductor is connected to a 24 volts 50 hertz main supply. If the current through the inductor is 1.5 ampere, calculate the inductance of the inductor. Now this is, when we're dealing with inductor, we're talking about inductive reactance, which is XL is equals to 2 pi F times inductance. So 2 times, they say we should use 22 over 7. Okay, no problem. 22 over 7 times frequency 50 hertz times inductance. Where is inductance? I can't see inductance. Let's say we should calculate the inductance of the inductor. So the inductance of the inductor is L. What is XL? The inductive reactance. If the current through the inductor is 1.5 ampere, there's supposed to be something in ohms for us to be able to calculate the inductance of the inductor, right? Okay, so they gave us the current through the inductor. Remember from Ohm's law, we had V equals to IR. You know this formula has appeared many times. V equals IR, so you must remember it by now. R is resistance, right? And reactance is also resistance. So I can change the formula to V is equals to I XL, right? So 24 volts is equals to the current 1.5 times inductive reactance. So inductive reactance is going to be equals to what? 24 divided 1.5, and that's going to give me what? 16 on the dot. So 16 ohms is our inductive reactance, and that's what we use here. So simplify 44 times 50 divide 7, 2200 divide 7, we have 314.3 approximately. So L is equals to 16 over 314.3. We're going to get 0.051. This is equivalent to 5.1 times 10 raised to the power minus 2 Henry. That is the unit for inductance. So this is correct. Impedance. So this is the net reactance offered by a resistor, inductor, and or a capacitor in an AC circuit. Impedance is also measured in ohms. So what does this means? Just remember the formula. In an RLC circuit, in an RLC circuit, impedance is equals to square root, a big umbrella, square root, resistance squared plus, in bracket, inductive reactance minus capacitive reactance, close, squared. That's one formula for RLC, where you have a resistor, an inductor, and you have a capacitance, inductance, and resistance. Then for a circuit where you have only resistance and capacitance, you just remove this, and you have your new formula. Sorry, you just remove one of them, and you have your new formula. Same thing for this. So that's it. Resistance of a series RLC circuit is 5 ohms. If the impedance of the circuit is 13 ohm, calculate the reactance of the capacitor. So the reactance is given by what? The reactance of the capacitor is given by what? XC. But we're given impedance in this question. And impedance is what? Square root of, it's a RLC circuit, so it has to be what? R squared plus XC squared. So since we are given impedance as 13 and square root of our resistance was given as what? 5, so 5 squared plus what? What's going to be our XC? So an easy way is to just square both sides. I think I already know what my answer is. My answer is going to be 12 ohm. Square both sides, 13 squared is equals to 5 squared plus XC squared. XC squared is equals to 13 squared minus 5 squared. So this is going to give us capacitive reactance. Take the square root of both sides, right? 13 square is what? 13 square is 169. That is 13 times 13. 5 times 5 is 25. That's going to give us 144. Square root of 144 is 12. So our answer is 12 ohms. Next. A series RLC circuit, another RLC circuit. Wow. Determine the current passing through the circuit. Okay, whenever you see current in simple AC circuit, just know you have to relate it to Ohm's law. So V equals IR. In this case, it's a capacitance, so we have to relate it to capacitive reactance. Okay, so they said we should determine the current. This is the formula we're going to use to determine the current. The reactance, capacitance of reactance, 40 ohms, right? And what we're given a 30 ohm resistor. Wow, that means we have to find impedance first. Remember, this R here is the total resistance in the circuit, the net resistance. So we can also say V is equals to IZ. So we have to find impedance in the circuit plus XC. So this is 30 squared plus 40 squared. That's going to give us 900 plus 4 times 4 is 16. That's 16 square root everything. 16 plus 900 is 25. So square root of 25 is 550. So 50 ohm is the impedance in an ROC, in this ROC circuit. So that we can apply this formula here. So V, we're given 200 volts, 50 hertz. There's nothing we can do with the frequency. So, 200 is equals to the current times the impedance, which is 50. 50A1, 50A4. So the current is 4 ampere. An RLC series circuit consists of a resistor, inductor, and a capacitor. We should calculate the impedance, we should calculate the current in the circuit. Okay, so first of all, the impedance for RLC series circuit is going to be given by this formula: R squared plus, in brackets, XL minus XC squared. Alright, so impedance is going to be equals to, what is our resistance? 100 squared plus what? Our inductor is 0.05 Henry. This is our inductance. So we have to find inductive reactance. Remember, inductive reactance is 2 pi FL. So 2, they don't tell us what we should use pi. Let's just do it in terms of pi first. Okay, they give us pi as 3.14. So 2 pi, let's just do it in terms of pi first, times 50, which is the frequency, F, then L, which is the inductance, 0.05 Henry. So multiplying everything, our XL is going to be equals to 2 times 50, it's going to be equals to 5 pi. So 5 pi, I don't even know how to write this, 5 pi ohms. Remember, we have not substituted the value for pi yet. Then XC is equals to 1 over 2 pi F times capacitance. And so this is going to be equals to 1 over 2 pi, okay, times frequency times microfarad. We have to convert micro to farad. So in place of micro, write 10 to the power minus 6. So 50 times 25 times 10 raised to the power minus 6 farad. Okay, so I have to simplify from here. 2 times 50 times 25. Do that first. 2 times 50 is 100. 100 times 25 is 500. That's 10 raised to the power minus 6. Remember, the pi is still there. We have not substituted it yet. So 10 raised to the power minus 6. 1, 2, 3 is going to be 2.5 times 10 raised to the power minus 3. 1 over, we have to bring this up. It's going to be 10 raised to the power 3. We'll bring it up. And 1 divided 2.5 is what? 1 divided 2.5 is 0.4. 0.4 times 10 raised to the power 3. The same thing as saying 10 raised to the power 4 times 10 raised to the power 2 pi. So in terms of pi, XC is actually bigger. The thing is, we are just going to subtract anyways. Even if we get a negative answer, square will still give us. So 4 pi minus 5 pi ohms squared. So 100 squared plus 400 minus 5 is 395 pi. I think we can substitute pi now. 3.14 squared. So 395 . Wait, so something is wrong. Here, the pi was under, right? So how did it come to the top? So it's supposed to still remain under. So this is supposed to be like 400 over pi. I'm just creating complications for myself. I should have used that pi from the very beginning. Anyways, let's simplify quickly. So in place of pi, just put 3.14 there and get the answer. So in place of 400, I have 127.4 minus 5 times pi. 5 times 3.14 is 15.7. So 127.4 minus 15.7 is equals to what? 111.7. So we can square that. 111.7 times 111.7 is going to give us 100 times 100 is 10,000. So 10,000 plus this, and okay, so this is not a Jamb question. This is a eᵣε type question where you have to use scientific calculator. So let me just run down the summary of what we are doing. After we have gotten the square root of this, we'll get a value for impedance. Then to get the value of current, we're going to use the formula V RMS is equals to I RMS times what's the impedance. We get impedance, we use the voltage which we are given in the question, that is 220 volts, then we can get the IRMS correct. Resonance is said to occur in an AC circuit when the maximum current is obtained from such a circuit. The frequency at which resonance occurs is called resonance frequency, denoted by F0. For resonance to occur, maximum current must be obtained. The impedance Z must be minimum. Take note of that. And when this happens, inductive reactance minus capacitive reactance equals to 0. In other words, XL, that is capacitive reactance, inductive reactance equals capacitive reactance. Now, in the equation for impedance, you notice that since impedance is square root of R squared plus, in brackets, XL minus XC, since they are both equal, this would become 0. So 0 squared is still 0. We're going to have a minimum value for impedance, which is the value of resistance offered by the resistor or the load in the circuit only. So that's the minimum value for the impedance, and that's where resonance is said to occur. Now at resonance, because XL is equals to XC, we can equate their formulas. So formula for inductive reactance is 2 pi F times inductance is equals to what? 1 over 2 pi F times capacitance. From here on, we can cross multiply. Don't go and say 2 pi cancel 2 pi. That would be a blunder. A terrible blunder. So instead, you see 2 pi FL cross multiply. So you have what? 2 pi 2 pi is common, so we just say squared. F is common, so we say F squared. L and C, they are on their own, is equals to what? 1. So now we have to simplify. Let's make F the surrogate of formula. F squared is equals to 1 all over 2 pi squared LC. So to remove the square from frequency, we square both sides. We take the square root of both sides. So square root of F squared is F is equals to square root of 1 is 1. Square root of this, the cancels out the square, so we have 2 pi, and then we're left with what? Square root of LC. So we have this. This is the formula for frequency at resonance, or resonance frequency. This is the formula, so please take note of it. And also here we can also have that resonance angular velocity is going to be equal to what? 2 pi times the resonance frequency. The resonance frequency in an AC circuit is 1000 kilohertz. If each of the capacitors and inductors in the circuit is reduced by 50% and no other changes are made, the resonance frequency will become what? Okay, so this is a very technical question. Very technical question. First of all, in the resonance circuit, XL is equals to XC. That's one thing you need to note. And now they're asking us that if each of the capacitance and inductance in the circuit is reduced by 50%. So the capacitance from resonance frequency formula is given by what? 2 pi square root of L and C. So L here is the inductance, C is the capacitance, right? This is the formula for resonance frequency that we derived from this. Okay, so let's continue. If the capacitance is reduced by 50%, to reduce something by 50% is to multiply by 1 over 2 or to divide it by 2, right? So the new resonance frequency will be given by 2 pi square root of L over 2 times C over 2. Remember, we reduced the inductance and the capacitance by 50%, so we're halving both of them. That is reducing it by 50%. A wise thing to do here will be to square both sides. So take the square of both sides. So we have resonance square. 1 square is 1. 2 pi is going to come back to this, and then square root is out. So I'm going to be left with LC all over 4. Abi? There was no need. Okay, we can work with that. So the original frequency was what? 1000, right? The original frequency was F0, and this was the formula. So if we square both sides here, we're going to arrive at square. This cancels out as well. We're going to arrive at this 1 over 2 pi times what? LC. Now we're going to take the ratio of, or note what the change is between the new resonance frequency and the former one. So what I can note here is that if I take the ratio of FO to the new resonance frequency, 1 over 2 pi square will cancel 1 over 2 pi square. Am I right? That means we're going to be left with what? 1 all over LC over 4. So I'm going to be left with 4 over LC, right? And then here we're going to be left with what? 1 over LC. What is the difference between this one and this one? It just means that, okay, LC can also cancel out. So LC cancel out there, LC will also cancel out here. We have 4 and we have 1 here. That means the new frequency, the square of the new frequency is equal to what? 4 times the original resonance frequency squared. That's what it means. So resonance frequency squared, that is the new one, is going to be equals to 4 times the original value of 1000. So we take the square root, that's going to be 2 times 1000. That's going to give us 2000 kilohertz. That's the way I understand it. But there are better ways to solve it. For example, I did not need to square both sides. I could have just compared the former frequency to the new one directly without having to square both sides. Let me show you what I'm talking about. So this is the resonance frequency formula, right? 2 pi square root of LC. So the new resonance frequency, let's call it resonance frequency prime, is equals to 1 over 2 pi. We have to take 50% of the capacitance and the inductance. So capacitance over 2, inductance over 2, L over 2 times C over 2, square root of B. So we are going to end up here, root LC, 2 times 2 is 4, square root of 4 is 2. So we are going to end up with root LC over 2. This 2 is going to come up. So we are going to have F prime is equals to 2 over 2 pi LC. Compare this to this. What's the difference? The difference is that the new frequency is equals to 2 times the former resonance frequency. Because watch now, if you substitute FO here, multiply by 2, you see that we will get this. So this means this relationship we have created is correct. Therefore, we can say 2 times what? The 1000, we'll still get the same answer. This was the easiest approach. But I had to understand the question first before I came up with this easy approach. Important facts in RLC circuit to remember. 1. In a purely capacitive circuit, current leads voltage by a phase angle of 90 degrees or pi over 2 radians. Pi over 2 radians is the same thing as saying 90 degrees. Pi radians is equals to is equals to, what am I saying? Pi radians is equals to 180 degrees. 2 pi radian is equals to 360 degrees. Therefore, pi over 2 radian is like saying 180 over 2, which is equals to 90 degrees. And that is why the phase difference is also called pi over 2 radians. Note, in a capacitive circuit, current leads voltage. It is the opposite for purely inductive circuit. Now, if current leads voltage, it means voltage is lagging behind current. Please understand that term. You can just learn only the one for capacitive circuit. Then just know that for inductive circuit, you are going to change it. Now, it's going to be current lags voltage and what voltage leads current. Take note of the key the key terms. So just learn one, then always take the opposite for when you come to inductor. That's the best way to memorize this. Then number 3, the power dissipated in an AC circuit is given by P equals IV cos phi, where phi is the phase difference. So take note of this formula too. The power factor is determined by the cosine of the phase difference. That is the cosine of this value. For a capacitor and inductor circuit, the power factor is 0 because what? Either current leads voltage or current lags behind voltage by what? 90-degree phase difference. So cos 90 is 0. So power factor in capacitor and inductor circuit is what? 0. But for a resistor circuit, there is no lead or lag, which means the power factor is what? 1, because what? Cos 0 degrees what? 1. As simple as that. 5. Energy stored in an inductor is given by the formula 1/2 Li squared, where I is current, L is what? The inductance. Take note of that as well. Impedance is the total reactance. We already know this. We already know what happens at resonance frequency. Impedance can be calculated using RMS value for voltage and current. Never mix using RMS with peak. If you are using peak, please use peak with the impedance. If you are using RMS, please let the RMS remain consistent, but never mix both by using VRMS together with peak. For example, this is a blunder. Relationship between RMS and peak value for current. Remember this. Just easily use this to relate them. IRMS equals to 0.707 times what? Peak current. Same thing similarly for voltage. Okay, so look at this question. Calculate the energy stored in the inductor. What is the formula for energy stored in the inductor? 1/2 Li squared. So that's what we're going to do. The inductor, Henry, 0.1. 1/2 times what? 0.1 times current squared. What is the current? Current, they give us voltage, they give us what? Resistance. So V is equal to IR. We can use this to calculate for current. So I is equal to V over R. Therefore, 100 volts over the resistor will give us what? 1 ampere. So we can use that 1 ampere squared. And you see that we get what? 0.05 joules. This is the correct answer. Next one, the amount of heat generated in external load of resistance 8 ohm if an alternating current of peak value 5 ampere passed through it for. So we have to calculate the amount of heat generated. Now it will be wrong for you to go and solve and use H is equals to I peak arrow square T. Although this is a formula for heat, but using peak value for current is wrong because the effective value for current in an RLC circuit is what? The RMS value. So you have to use the RMS value to solve, not the peak value. Always remember that. So if we use RMS value is given as what? Our resistance is 8, right? Our resistance is 8, so 8 square, let me start with that. The time is 100 seconds, so 100 square times the current. The current should be RMS. How do we convert this to RMS? Any ideas? So RMS is equals to peak times 0.707. Therefore, we got peak value. We just have to multiply it by what? 0.707. So 5 times 0.707 equals 3.5, around 3.54. Why did I square this to start with? There is no square in time. So 3.54 times 8 square times 8 squared times 100 is going to give us 226.56 exactly. Okay, so that means we just have to use the peak current. Probably that was what they were asking for. I don't know, but if there was 2.2, 1, 2, 3, 4, 2.3 times 10 raised to power 4 joules, this would be my answer, because this is only a peak value. This is only a peak value. It is not steady. It increases to a peak 5 ampere and decreases, but the steady value is what is going to give us the heating effect. So I guess they wanted us to just use the peak value here. Thank God there's no option like this. But if there was an option like this, this would be the correct answer. So by that standard, the correct answer now becomes what? So instead of 3.54, we use 5 times what? 5 times 8 squared times 100. 3.2. So we are getting 3.32,000 from this, which makes it wrong. That means we're correct. So 2.3 can be approximated. We can approximate it as 2. Yes, we can. So this is actually the closest answer we've gotten. So next question. Calculate the average power dissipated in AC circuits with RMS current of 5 ampere and voltage and phase angle. So the formula to use here, if you remember, is P equals to IV cos phi. Well, I wrote theta instead of phi. Anyway, 60 degrees times I, which is 5, times voltage of 10, that is 50 times cos 60 is 0.5. That is 0.5. So our answer is going to be 25 watt. This is correct. Alright, so I've come to the end of this video. If you enjoyed this electricity summary video, don't forget to hit that like button and subscribe to stay updated when I upload more exciting content. Thank you. I wish you all inevitable success in your exams. You've got this. Peace, and I'm out.